Hello wonderful person, this is Anton, and today we're going to be talking about a discovery of a very interesting star system somewhere out there. The star system that has 6 very unique planets with an extremely interesting pattern of orbit around the star. The pattern that we usually refer to as orbital resonance, but in this particular case the resonance is very unique, something that we've never seen before. And so let's discuss this discovery in a little bit more detail, but also talk about resonances in general. And let's start this with a bit of a history trip into early astronomy. Back in the days, here we're talking about hundreds of years ago, the early astronomers realized that there was actually a bit of a pattern to the placement of planets in the solar system. So here, for example, if we were to take a look at the distance of Mercury from the Sun and then multiply it by 2, we would roughly get the orbit of Venus. Then multiply this by roughly around 2, and you get the orbit of Earth. Then you get orbit of Mars, and then there's an unusual gap. And following this gap, you get the orbit of Jupiter, followed by the orbit of Saturn. And back in the days, this is actually how Uranus was discovered as well. Because of this unusual prediction, scientists estimated that there was actually another planet somewhere out there. But this pattern obviously doesn't work with Neptune and with anything past Neptune. However, interestingly, because of this pattern, the scientists were also able to discover Ceres and a lot of other objects we refer to as asteroids in the asteroid belt. They initially thought that this was a missing planet, but we now understand that this is not a planet, and we also know that the asteroid belt might actually be a remnant from the early formation of the solar system, but because of the influences from Jupiter, it never really became a planet at all. Nevertheless, there is a strange pattern and a strange correlation with distances away from the Sun, and to some extent this can be maybe used to determine certain other patterns in other star systems. The one in the solar system actually has a name, and I made a video about this a few years ago. It's known as this law right here, and it is accurate to some extent, but obviously has a few exceptions that don't really make any sense, like the orbits of Neptune and of course the orbit of Pluto and other objects. But when it comes to orbital patterns, we know that there is something called orbital resonance, and the best example of this is right here in the solar system around Jupiter. The first 3 moons of Jupiter form an exact orbital pattern of 4, 2, and 1. In other words, for every 4 orbits of Io, Europa is going to make 2 orbits and Ganymede is going to make 1 orbit. And these orbital resonances have actually been detected in many different places and also do play a very important role in our understanding of the formation of various systems. Today we think that, or at least we believe that, they usually develop as the material orbiting something moves closer and closer to that object, and the material itself stabilizes the overall mass of all of these objects to form these patterns in order not to disrupt anything else in the system. In other words, this is a stable formation of an orbital system as it sort of reshuffles around some sort of a central object. And it's possible that this is exactly what happened in the solar system with these various patterns we're observing, but in this case, Jupiter, because of its sheer mass, is also able to disrupt certain patterns and actually does influence and change the solar system over a period of billions of years. But because we know these resonances exist and because we know they're very important for the stability of a system, discovering these patterns in other star systems, such as the famous TRAPPIST-1, helps us understand whether there are any other potential hidden objects in this particular system, and also helps us understand how these systems evolve. Now in TRAPPIST-1, the resonance is also there, but it's actually a lot more complex, with relatively complex ratios forming between the orbits of these planets. Although overall these ratios are extremely close to 1.5, which means that for every 3 orbits of the closer planet, the more distant planet is going to do 2 orbits. And this is a really important resonance because first of all it's extremely common, second of all it usually shows us that this particular star system is relatively stable, but because of the deviations in these patterns it also allows us to discover other massive objects. Which is why it's really important to analyze this particular system, located around 88 light years away from us, where 6 different planets form a very interesting and extremely precise orbital resonance that actually can help us explain a lot of things about the star system, but also help us understand how to analyze other star systems as well. So in this particular case, we have an interesting star very similar to our own Sun, where 6 planets seem to be orbiting extremely close to the star itself, with each of these planets being defined as a kind of a super Earth or some kind of a Neptune-like object, but in this case, really hot super Earth and really hot Neptune planets. Based on the masses and the sizes of these planets, the estimates so far suggest that about 5 of them are essentially these Neptune-like worlds, and possibly 1 is a super-Earth, with the smallest planet being about 2.2 masses of planet Earth, and the largest one being more massive than Neptune itself. In other words, even though the star in this system is similar to the Sun, everything else here is extremely different from any other system we've observed so far. All of the planets here are really close to the star. The orbit of the closest planet here is only about 2.17 days long, and that makes this planet extremely hot, obviously. But what's interesting though is that if you were to multiply that value by 1.5, you would get the orbital period of the next planet. Do this again and you get the 3rd planet, and then the 4th planet, and then the 5th and the 6th. And that's where things become really interesting, because the orbital resonance of 3:2 applies to each of these 6 planets, with the last planet having an orbital period of about 17.5 days. Now that's obviously about 4 times closer to the star than Mercury is to the Sun, which makes each of these planets extremely hot, especially if they have thick atmospheres. But because of this unusual 3:2 resonance amongst all of the planets, it also obviously creates an extremely stable system that's going to stay stable for possibly billions of years, until I guess these planets evaporate completely. And you can kind of see that even in this simulation, their atmospheres are evaporating extremely fast, which also suggests that only the core of these planets is going to remain in the next few billions of years. But just like with the other resonances, this also means that a lot of these planets probably formed somewhere on the outskirts of the star system and slowly migrated toward the star, where they eventually settled on these very specific and very stable patterns. Today we believe that this usually happens as the planetary system where the planets develop interacts with the remnant of the gas in the disk itself, pictures of which we have from many different young star systems out there, like this one right here known as HL Tauri. And so as the planets migrate through the disk and as they essentially come closer and closer to the star because of the interaction with all of this dust here, they eventually stabilize in certain orbital patterns similar to the ones we observed in systems like TRAPPIST-1 and Kepler-80. But in this particular case, none of these resonances are perfect. In most cases, they have slight deviations from the usual 3:2 or 2:1 resonance. And this can be actually explained by all sorts of different instabilities introduced into the star system as all of this gas dissipates and the actual planetary system is born. And so because of these imperfections in the orbital resonance, we can actually use this to try to determine the initial mass of the protoplanetary disk from which this particular star system was born. And if we're able to do it for this particular star system, this in turn can help us analyze our own solar system and thus discover what the protoplanetary disk of the Sun looked like. In other words, it can help us see the history of the solar system if we can actually figure out how all of this works in other star systems as well. At the same time, these inaccuracies in resonance kind of point at various mass discrepancies and of course composition and mass of each of these planets. So in that way we can also use these patterns to try to analyze what all of these planets have on the inside. But all of this is of course in the future. For now, all we know is that this interesting star system, at least for now, seems to be the only system out there with the most perfect resonance of all of the objects out there, with the orbital resonance between each of the planets being almost exactly 1.5. So once again, for every 3 orbits of the closer planet, the farther planet is going to orbit twice. And because this applies to each of the 6 planets here, this actually makes this an extremely interesting star system to study and also an extremely valuable source in learning how star systems and of course solar system developed over time and progressed from being just a cloud to then being a disk with protoplanetary objects to then eventually becoming a star system with planets in a very specific region. And because so far we only have a few star systems out there that we know of that have more than 5 planets in them, including TRAPPIST-1, Kepler-80, and now HD 158259, and every one of these planets seems to possess some sort of a resonance, it's also important for us to learn how these resonances influence planets in order for us to be able to discover other planets much easier. Which is, by the way, how one of the planets here was discovered to begin with. By looking at these patterns, the scientists realized that there was another object hiding in the data. And so once we figure out how these patterns work, and more specifically what type of a pattern to expect from a certain star, we might be able to find planets much easier and also much quicker. For now though, this is a very interesting discovery, definitely a star system that we kind of didn't expect to find, and also a star system that just seems extremely different from the solar system despite the similarity with the Sun. But until future studies, that's unfortunately all we know about the star system and about these residences. Hello wonderful person, this is Anton, and today we're going to try to answer a question of oxygen in some of the planets we might find in the future. So imagine for a second we discovered oxygen on this planet known as TRAPPIST-1b. What exactly does this mean? Does this mean we just found life? Is this oxygen created by some sort of bacterial life? Or can this be what's known as a false positive? Can this be just a sign of some sort of a chemical reaction? Well, naturally the answer is yes, but what kind of a reaction and what exactly should we be looking for? And so that's pretty much what this particular paper wants to answer. They used several computer simulations to try to create various types of planets similar to planet Earth, orbiting a star similar to our own Sun, with very minor modifications of how many different types of volatiles or how many different types of gases are present in the early atmosphere. And then they try to discover if any of those planets can actually create conditions with a lot of oxygen that's not produced by life, that's produced naturally through geochemical reactions. And so interestingly, they've discovered at least 3 scenarios where it's possible, 3 false positives. And considering the fact that we've already discovered and confirmed over 4,000 exoplanets, the number that's going to become about 10,000 in a few years from now, and also considering the fact that new telescopes such as James Webb that's going to be released later this year are going to be really good at finding these molecules, it's super important for us to be able to identify all sorts of different molecules present in the atmosphere of those planets in order to establish the origin of those molecules. With the main emphasis of course being oxygen, because we know that oxygen on our planet is produced by life, and if we find a planet similar to Earth that has oxygen, does that mean life as well? And so the scientists in this paper argue against that because they do provide evidence for potential Earth-like planets to have oxygen with really no life whatsoever. But first of all, how would the oxygen be even produced in these conditions, especially when there's no life? Well, generally speaking, as long as you have a little bit of water somewhere in the atmosphere, maybe on the surface, and as long as there's something going on that can break down this water, which in this case usually means the presence of ultraviolet radiation coming from the star, the water will always break down into hydrogen molecules and oxygen molecules, with hydrogen escaping into the outer space because it's a much lighter gas, but oxygen very likely just sticking around for a while, and in some cases sticking around for several million years. Now in most cases though, it is going to be absorbed by something. So for example, let's just say we take this hypothetical Earth with very similar conditions to actual Earth a few billion years ago, and for a few billion years let it evolve. So it's going to have a lot of geochemical reactions, it's obviously going to cool down and so on, but unlike actual Earth, it's going to be a little bit different. In this case, this planet seems to have a lot less water than original Earth. It's kind of patchy in that sense. In this case, the scientists refer to this as the desert world. Now you might actually see this as something a little bit familiar. It does look like the model of that Mars that I've talked about in one of the previous videos, and that's exactly what the scientists imply here. A patchy desert world will actually have very similar conditions to early Earth, and will even start producing oxygen as well through geochemical reactions. In this case, because there was a lot less water present on the surface, as the planet cools down from the initial magma stage, it's going to end up releasing a lot of this water as the atmospheric water. And as all of this atmospheric water accumulates, it ends up being broken down by the star, and this produces a lot of oxygen that very likely lingers in the atmosphere for a very long time. Now, eventually this oxygen starts being removed, usually through various geochemical reactions. For example, through various volcanic activity that might release things like carbon monoxide and hydrogen, which might combine with oxygen, creating a little bit more water and a lot of carbon dioxide, while at the same time most likely also influencing the surface as well. All of this oxygen ends up weathering the surface, turning it somewhat red to what you see right here on the surface of Mars. So in other words, this is a very interesting model representing what might have been happening on Mars a few billion years ago. But in contrast, if you were to look at our own planet, once the water condensed on the surface, all of this water sort of remained here. The escape rates and the production of atmospheric water were much lower than they were on those other desert planets. And so those desert planets tend to produce a lot of atmospheric water, which then starts to break down into oxygen and remain in the atmosphere for up to about 1 million years. But remember, none of this is related to life at all. It's just a geochemical reaction. And so this is if you start with a little bit less water. But then you can have a condition where the planet starts with a lot more CO2 compared to everything else. This is a slightly different scenario because here you end up with an atmosphere that's much hotter than usual. And because of this greenhouse effect, which in this case the scientists refer to as the eternal runaway greenhouse effect, you end up with a planet where the atmosphere is predominantly carbon dioxide, but also has a little bit of water and starts forming a lot of oxygen as well. And all of this oxygen comes from the fact that any water that was present here could not create any liquid on the surface. The planet was just a little bit too hot. And so it all ends up being as atmospheric water, and because CO2 is a little bit heavier than H2O, H2O starts to move to the top of the surface of the atmosphere. And right there on the top, that's where the star once again starts to break it down into hydrogen and oxygen, and the same cycle repeats again. Although in this particular case, it's very likely that there are not going to be a lot of opportunities for this oxygen to become integrated into something else. It actually might remain as oxygen for even longer, maybe millions, maybe billions of years. And you might have guessed already, but this is exactly what we think might have happened to Venus. Venus, as you know, is extremely hot because of the presence of CO2. Venus also most likely had a little bit of water in the past. And today we know that Venus seems to lose a little bit of oxygen from the surface. This oxygen could be coming from the water that's still somewhere on Venus. And so all of this kind of starts adding up to what we probably had in the past in the solar system. We had a planet with a lot of CO2, we had a planet with the lack of water, and then we had Earth that seemed to have conditions necessary for life to form. But the thing is, what if you find a planet that has even more water than Earth? So that's the third scenario. Imagine a planet that has very similar everything, but just has way more water. A water world. Well, this water world will have a lot of oxygen and nitrogen on the surface, but it's also going to have a huge presence of water that's going to create a lot of pressure, very likely completely shutting down all of the geological activity on the surface. No plate tectonics, very few, if any, volcanoes, and thus inability to recirculate certain parts of the atmosphere. So because of all of this water on the surface now, the oxygen cannot actually get integrated into rocks like it did on Mars. And obviously the water vapor is produced in really large amounts, the water is still being broken apart, and more oxygen is being produced everywhere on the planet. There's also not a lot of volcanic activity, and because of this, not enough carbon monoxide is produced to try to capture more of this oxygen. And so what you end up having is a planet extremely rich in oxygen, at least after a few millions and billions of years, yet none of this is produced by life. It's really just produced by the water on the surface that's being broken down by the UV light coming from the star itself. And although this planet might resemble a habitable world, and might actually fool us into thinking that there is life here, there's nothing alive about this planet. It's all just chemical reactions. And so these three conditions ideally show us that you can start with an Earth-like world with slight modifications and end up with oxygen in all three conditions, yet no life whatsoever. Three very important false positives. Yet at the same time, if you were to take Earth and to have Earth with exact parameters as we have today, which scientists do in their paper as well, and then run the simulation for billions of years, you would not have oxygen on the planet. All of the oxygen produced on Earth is definitely from life. And we know this as a fact mostly because of the observations from various minerals, from various investigations of fossils in the past, and we even know that some of the oxygen on the planet was very toxic to early life. So by finding oxygen on any of these planets, we might actually reconsider the idea of seeing life there. Generally speaking, oxygen is sort of toxic. Fun fact, if you pressurize oxygen to, I believe, about 4 atmospheres, it also becomes toxic to humans, which is kind of counterintuitive. But that's a fact that's known to pretty much most scuba divers. You are absolutely not allowed to breathe pressurized oxygen because you're basically going to suffocate. This is actually known as oxygen toxicity, and you can kind of learn more about this from the link in the description below. And so the important implications from this study is that when we're looking at those stars and those planets using new telescopes such as James Webb Telescope, we really have to look for other wavelengths of light as well, making sure that we identify all of the possible molecules in those atmospheres. If there's oxygen, does it also have a lot of CO2? Are we also seeing the presence of some other molecules that would indicate that all of this is just geochemical reactions? And a lot of these new studies that are going to be coming out about this are very likely going to determine exactly what proportions to look for and what type of molecules we should be looking out for if we actually want to identify a planet as potentially living and habitable, or just a very interesting, completely natural and uninhabited planet that just happens to have oxygen on the surface. And with so many different planets already discovered and so many different planets that are going to be analyzed in the upcoming missions from the James Webb Telescope, we're definitely going to be finding these oxygen planets all over the place. And I can guarantee that in a few years you're going to hear a story about discovery of oxygen and thus life on another planet. But that is why we have to be really careful when we do discover certain molecules in certain atmospheres. Studies like this, identifying exact false positives, are very important in identifying what is it that we found and what created that certain element on that certain planet. Hello wonderful person, this is Anton, and today we're going to be talking about the mysteries of outer space. And actually the mystery in this case is going to be the discovery of some other unusual rogue planets. Because even though we technically think that the space out there is more or less empty, in reality the interstellar space is actually filled with various unusual objects. Anything from various types of dust and various types of clouds that seem to be all over the place, with the biggest one being the local interstellar cloud that we're currently flying through, to a lot of other unusual objects such as large asteroids, large comets, and probably a lot of planets, something that we've been discovering more and more of by using various missions and various telescopes, with the best example being this right here, OGLE, Optical Gravitational Lensing Experiment, ran by Polish scientists but located in Chile. But since the majority of these objects are extremely dark and have no illumination of any kind, it's naturally almost impossible to see them. And so the only technique we know of that effectively finds these unusual objects out there is the technique using gravitational lensing, which is exactly how the majority of rogue planets, or planemos as they're also known, have been discovered in the last few years. With some of the other ones, like the first one ever found, OTS-44 that you see right here, being discovered because they do emit a little bit of infrared light that we can actually see by using very powerful telescopes. Here's another one with the name you see right here, that was discovered back in 2013 by essentially looking at it in infrared light. Now the closest one to us that's confirmed is at a distance of about 80 light years away from us, and so we haven't really found anything in the nearby vicinity. And because of this, there are essentially two major methods of detecting these. Either we look for these larger brown dwarf-like objects that seem to emit a lot of infrared light, which technically should not really be classified as planets because they kind of belong to their own class. These are really more brown dwarfs than planets. Or we can occasionally find them when they pass in front of a distant star and bend the light in just the right way, producing the optical lensing effects. Now these are the ones that are most interesting, mostly because it allows the scientists to measure their mass quite precisely. And these are the ones we're going to be discussing today because the recent study was able to identify 27 separate optical lensing effects, suggesting that they discovered rogue planets. But a lot of these have already been confirmed by some of the other studies, so they're not new discoveries. In this paper, however, they did identify something that was not seen before. They found several planets that seem to be, overall, quite similar in mass to planet Earth. And this is what makes this study particularly intriguing. They discovered several Earth-like rogue planets. And since the first Earth-like rogue planet was discovered only a few months ago in October of 2020, this makes the study extremely intriguing. So first of all, from some of the previous discoveries, especially the ones that involve brown dwarfs, the scientists realized that these objects can definitely be created in a somewhat similar manner to a typical star. They are made from a molecular cloud material and they essentially coalesce into a protoplanetary disk. In this particular case, this disk was discovered to be approximately 10 Earth masses in mass, which means that this rogue planet or this brown dwarf eventually will have its own moons as well. But since it's only about 12 million years old, it's still developing even now. But then there are these other objects, the much smaller ones, or the objects that do not really qualify as brown dwarfs. Now these have a very different creation story. In this case, they most likely just got kicked out of various star systems. Now we do believe that there was an extra planet in the solar system, for example, based on various simulations, and this planet was probably also kicked out as well. And so these types of planets are the ones that are most interesting because they are actual planets. They were probably created in various star systems, but through the interaction with other objects in the star system, eventually became their own travelers. And the thing is, current analysis suggests that there are at least 100 billion of these, possibly even more, possibly even trillions of these in the galaxy itself. And so if we were to look at this map again, where the sun is located, according to these theories, there should be tons and tons of these rogue planets located between all of these stars, floating around without being seen simply because they're just a little bit too small and definitely too dark. But in this particular study, the scientists did something that hasn't really been done very well before. They used the data from a telescope that was never meant to study rogue planets. They used the data from the famous Kepler telescope. As you might be aware, the main purpose for the Kepler telescope was to literally just look at the same spot in a galaxy for a very, very long time in order to detect various tiny shadows passing in front of distant stars. It was looking for the transits of various exoplanets, which allowed it to discover several thousand exoplanets over the last few years. And so the scientists behind this study decided to apply an algorithm looking for a very specific observation. They wanted to find something that would produce the observation resembling this. When a somewhat bright object passes in front of some sort of a mass, it's going to produce the landing effect with an extremely specific increase in brightness representing this, the Einstein's lens. And depending on the mass of the object, it would last anywhere from a few hours to possibly a few days. So for example, a brown dwarf-like object would produce something that would last maybe up to about 10 days, with an Earth mass object producing something that should only last for a few hours. Which of course also means that it would be a lot more difficult to detect these low mass objects. And so by using the data from approximately 2 months of observations of Kepler telescope, they've definitively identified 27 different signals using this new algorithm. But in those 27 signals, the majority was already known from some of the previous studies, from some of the previous observations. But 5 of them were completely new and have never been seen before. Here's what all of this would look like if you were to actually look at this in the data. So these 4 right here are relatively similar, at least in terms of the potential mass, and they do seem to represent a mass that's very similar to planet Earth, with the 5th candidate being really intriguing and somewhat interesting, almost as if this is some sort of a binary system. Here's another look at all of this from a slightly different graph with a little bit more analysis. So the 4 candidates here seem to be more or less the same, with the last 5th one being slightly more unique. And since prior to this we've only really seen one other Earth-like rogue planet, this does present a super interesting opportunity to study this further. But the problem is that we'll probably never see these objects ever again. Statistically speaking, they might have another gravitational landing effect in the next million years or so, which means that we're not going to be seeing these exact objects. But we might be able to detect a lot more of them when the new telescopes, such as for example the Nancy Grace Roman Space Telescope, become operational in the next few years. And so by applying the same technique, by using the same algorithm, and very likely the same observational technique, the scientists could now potentially discover hundreds and maybe even thousands of these rogue planets flying through the emptiness of space in complete darkness. For all we know, we might actually be really surprised at the numbers we discover in the future. And we might also realize that space is not so empty after all. But I guess the cooler part of this particular study is how they managed to use the old data from a telescope that no longer even operates to find something that it was never meant to find to begin with. They managed to use the data and mathematical analysis to almost look for the opposite of what the telescope was built to do. Normally it's supposed to find dips, but in this case they managed to find these brightening events that can only be caused, or at least can generally be caused, by something like this. And so chances are that this particular technique is definitely going to be used again to try to discover even more of unusual planets using some of the other data from, for example, a TESS telescope. So only future will tell what the scientists discover. But until then, I guess that's all I wanted to mention. We don't really know, or will probably never know, what kind of planets these are, other than maybe predicting their total mass. And just knowing the mass is just not enough to determine anything else. And because there's only one observation, that's unfortunately not going to tell us anything. And so because of this, for now at least, that's all I wanted to mention about rogue planets and recent discoveries. Hello wonderful person, this is Anton, and today we're going to be talking about a potential discovery of a pretty exciting planet around an iconic star. A star that all of you might have seen in the night skies, a star known as Vega. So in some sense, we might have discovered a vegan planet. Yeah, not a vegan, a vegan planet. And in this case, the planet itself might be super extreme. But let's actually talk a little bit more about this, because if confirmed, this is going to be a very exciting discovery. Now, first of all, as you probably know already, we've discovered over 4,000 different planets already as of 2021. Most of them were actually found this way, by looking at the shadows. But some of the iconic stars like Vega, stars that are extremely bright and very well studied, surprisingly seem to not contain any planets around them. Vega is only about 25 light years away from us, and it's also one of the brightest stars in the night sky. So bright, as a matter of fact, that it's visible in twilight, and it's also visible in light polluted areas, which actually allows the scientists to study it from anywhere on the planet. And apart from our Sun, it's the second most well studied star out there, which means that in the last few years we should have found something around it. And in the last few decades there have been a few reports of potential planets here, but so far all of them have been more or less discredited for one reason or another. Here's actually the artist's impression of what the planet here might look like. Now, interestingly, look at the star itself. It's very unusual in shape, and obviously it's very bright and very different in color from our Sun. And that's because this is what it looks like compared to our Sun. As you can see, it's sort of egg-shaped. Now, you can probably guess why this is so. That's because it spins really fast. For our Sun to go around its axis once, it usually takes it about 25 days. But this much larger and more massive star only takes about 16 hours. And because it spins so much faster, it basically got flattened over time due to the centrifugal forces from the relatively fast rotation speed. But because it spins so fast, it also possesses some other extreme effects. One of them is related to its magnetosphere. It's very likely that this star has extremely powerful magnetic emissions, and this is one of the discoveries in this paper as well. And it's also a much younger star than our Sun, and has about twice the mass of our Sun, which also means that it's not really going to live as long. Because it's so much more powerful and because it emits so much more light, it's going to reach the end of its life much sooner as well. But for decades, even though the scientists kept looking at this star and trying to discover any kind of shadows of planets passing here, they couldn't really find anything. And for many years, the speculations about the planets around the star have been going on, but there was no actual proof. But here's the thing though, using a different method known as radial velocity, and by essentially looking at the star as it wobbles around a central point, and also by combining this with 10 years worth of data and observations, the scientists might have actually found something after all. And that something is a planet, but it's extremely close to the parent star, with the orbit roughly looking like this. And because it's so close to the parent star, and because the star is already more massive and more powerful than the Sun, this means that this is an extreme planet. The temperatures here suggest that it's probably the second hottest planet ever discovered, with the temperatures on the surface reaching 3000 degrees Celsius or about 5400 degrees Fahrenheit. And that's actually hotter than some of the stars we've discovered out there, and that is absolutely extreme. The data also suggests that this is probably some sort of a Neptune-like planet with the mass of about 20 masses of planet Earth, and a single orbit only taking about 2.43 days, suggesting of course that this planet is very likely tidally locked to the star, meaning that a single side is always pointed toward the star, with the other side always being in darkness. And the scientists know all of this simply by looking at the wobble of the star across those 10 years of observations. Here they noticed that the star was wobbling by changing its velocity around the central point by about 6 meters per second. In other words, something was causing the star to change the velocity by this much. And all of this was happening every 2.43 days. Here's actually a rough simulation of what all of this looked like. Notice how as the planet orbits around the star, this velocity graph changes as well. Now in this case you'll notice that it's about 9 point something meters per second. That's because I actually chose a planet that's a little bit more massive. But by adjusting the mass a little bit, you'll notice how the graph here will fall down to the amount that they discovered. And so here with a planet of about 12 masses of planet Earth, the velocity is roughly around 6 meters per second, just as they've discovered in their study. And this particular technique is very well known and very well understood, so there's actually very little in terms of interpretation of what's possibly happening here. But in this case, we're looking at this orbit if it was completely aligned toward us. The thing is, we don't really know exactly what the inclination is, and so the minimal mass of this planet is probably around 20 masses of planet Earth. That's according to the scientists behind this paper. With this object that I guess we can refer to as hot Neptune, most likely also being extremely inflated and possibly even larger than Jupiter in size, simply because of the extreme heat generated here, with the heat being so high that it most likely also evaporates metals. So the atmosphere here very likely contains a lot of things like irons and nickels and a lot of other stuff. It's one of those planets where it's actually raining metal. But unfortunately, because this star is so extremely bright and so extremely powerful and also spins so fast, a lot of signals and a lot of observations coming from this object are somewhat difficult to analyze because the star actually produces so many frequent variations and it's a variable star as well. And so even finding this object and discovering the patterns in the light coming from the star was actually extremely challenging for the scientists. But also being the 5th brightest object in the night skies, this is one of the most important stars out there. And so finding a planet in this star system would actually be a huge revelation. So in this case, it's probably one of the more important discoveries of the year so far, assuming of course it's confirmed. But because the star system is only about 500 million years old, and also since it's already halfway through its lifespan, it means that the planet here is definitely much younger than anything we have in the solar system and will probably perish by the time the star starts expanding and turning into a giant. And apart from the potential planet, the scientists also discovered a potential magnetic variability of the star. It seems that approximately every 0.6 days, it seems to have some sort of a variation of the magnetic fields, which implies that its magnetosphere and a lot of activity on the surface here changes quite a lot, approximately twice per day. And this would of course imply that this is not a star you would want to live around because it changes way too much and it's just extremely unpredictable. And so finding any kind of a life around the star system or especially on this planet is most likely out of the question. But if this planet is really there, the scientists in the paper suggest that there's probably a pretty easy way to confirm it. It's actually using another method known as direct imaging. That's when you cover the star itself and try to look for a very hot, very bright object next to the star. Because this particular planet is so hot, it should be visible pretty quickly and we should be able to see it using some of the modern techniques. But whether there are other planets here is of course another question. One thing that we know about the star system already is that it does seem to have a debris disk around it. So in some sense, something similar to the asteroid belt that we have in the solar system. But this debris disk seems to be more or less flattened and also quite smooth, which actually suggests that there's probably no other massive planets in the system. Any other planet present in the system would have skewed the disk or possibly disturbed it in some other way. Although interestingly, the creation of this disk is another story. It has been implied that it was created by a collision of two different objects, possibly planets. Which of course obviously suggests that the planets used to exist here, but then turned into this very large disk. But does it actually have at least one planet? Well, that's of course another story, something that we'll probably learn in some of the future studies. Interestingly though, Vega is actually the second photographed star ever, after the Sun. And because of this, it's also one of the most well-studied stars out there. And the fact that after decades and decades of looking, we haven't actually discovered any planets here until now does imply that maybe, just maybe, this particular planet is also not there. Maybe it has some other explanation. So this is why future studies are needed to discover what's really happening here. And also, just a fun fact, about 12,000 years ago, this was also the northern star of our planet. It was pointing directly at the north. And it's also going to become the northern star in the next 13,000 years or so. And so in that sense, if the humans are still around 13,000 years later, we might actually think of the star in a completely different way. But I guess for now, that's all we know. It's a really cool star. It might have the second hottest planet we've ever found, and it also might have a lot of other mysteries around it, something that we can't really answer just yet. Some of the future studies might help us answer the question of whether this planet is real or not, but for now we don't really know. Hello wonderful person, this is Anton, and today we're going to be talking about this really interesting and somewhat intriguing planet that was discovered back in 2018 and about which we've learned quite a lot in the last few years. The planet that seems to be the first confirmed candidate for having what we refer to as tectonic activity. In other words, this planet probably has a lot of volcanoes and also possibly even plate tectonics similar to planet Earth. But let's talk a little bit more about this planet and about how the scientists discovered all of this, starting with some of the parameters we know about this planet and what it might sort of resemble. We know that this is a planet that seems to have absolutely no atmosphere or extremely thin atmosphere. It's also extremely dark, possibly similar in color to Mercury, with somewhat dark and non-reflective surface. The temperatures here are also relatively high on one side and super low on the other side. And that's because this planet is, first of all, completely tidally locked to its parent star, which of course suggests that one of the sides is always pointing toward the star and the other side is always on the dark side, with the average temperature right here on the bright side being about 770 degrees Celsius or about 1400 Fahrenheit. With the dark side possibly being close to absolute zero. And with a single orbit here only taking about 11 hours, and with the planet itself being about 1.3 times the size of planet Earth, this is actually a somewhat unusual and somewhat interesting object. It's a terrestrial planet, but it's extremely close to the parent star, and thus has very unusual and obviously super extreme conditions on its surface, something that we don't have in the solar system. Now, the best artistic representation of what the surface most likely looks like is right here. And this is of course based on several studies that establish that there's most likely no atmosphere, and this is a very non-reflective dark planet. But this is actually lacking some of the more recent discoveries coming from the simulations described in the paper you can find in the description. But I guess the question here is, how do we possibly know any of this? Well, by looking at the planet and also by looking at the reflections coming off this planet, and specifically what's known as the phase curve, the scientists for the most part were able to figure out the atmosphere and the reflectivity of the surface. For example, here is what the phase angle or the phase curve looks like for Venus and for Mercury. And so here, by looking at Venus from planet Earth and also by looking at Mercury from planet Earth, and then by comparing the phase angle, which is described in this picture, with the total magnitude of the planet, we can actually start seeing some interesting patterns. For example, for Venus, for the cloudy planet, you'll notice how it's much more shallow, and it actually has this unusual brightness excess right here, usually due to the reflections from its cloud layer. For Mercury, it has no clouds, and it's also a really dark planet, so it has a much more steep phase angle, which is even more steep than planet Mars. And by using this sort of analysis and by essentially comparing this to what we know about other planets, the scientists can usually determine what the exoplanet might actually contain on its surface as well, or at least if it has clouds or no clouds, and if it has very dark regolith or dark rock, or if it has reflective surfaces. And by using this sort of analysis and combining it with numerical and computer simulations, and by simulating various types of tectonic materials and also various types of heat sources, the scientists were able to establish that this planet very likely has a lot of volcanic activity and potentially even other types of tectonic activity on the surface, with one of the better representatives of what it might look like being this moon right here known as Io, the moon of Jupiter. Although here the number of volcanoes and also just the sheer number of activity is most likely much smaller than it is on this particular planet. And what's even more interesting here is that the scientists established that all of this activity very likely happens on just one side of the planet. They're not entirely sure which side though, but they kind of think that it's probably on a side closer to the sun or closer to the star. Which of course implies that one of the sides looks something like this, possibly even more extreme, with a lot of volcanoes everywhere, yet the other side being extremely different and potentially even completely devoid of volcanoes. But unlike on planet Earth, the simulations here suggest that the flow of matter inside the planet most likely does not really circulate up and down like it does on planet Earth, as you see in this particular picture, but instead seems to circulate across the entire planet. And in this case, on the hotter side, it's most likely going to be flowing upwards, whereas once the material reaches the other side of the planet, it might actually start flowing downwards. Which suggests that there's probably a lot of volcanic activity and a lot of tectonic activity closer to the surface facing the star. But that's not entirely certain because simulations actually have showed the opposite as well. And so on whatever side the material is moving upwards, that's the side where we would expect a lot of volcanic activity. In this particular illustration, the artist decided to put the volcanoes on the dark side of the planet. And interestingly here, you can even see all sorts of emissions on this side, with the side facing the star itself being extremely dark and empty of anything. But once again, what side has the volcanoes is actually not certain because we can't really see this just yet. And this is of course very different from what we see on, for example, Io, which has volcanoes pretty much all over the surface, and it's also somewhat different from planet Earth as well, even though on our planet we do have certain locations where there are more volcanoes, such as for example in Hawaii or in Iceland. But at the same time, there is actually at least one object in the solar system that might have experienced something extremely similar, and sometimes we get to see this object pretty much every single day. That object is of course our moon. And today we know that the moon's surface, the one facing planet Earth, has actually undergone a tremendous amount of volcanic activity. Some scientists have even suggested that some of the recent volcanic activity was about 100 million years ago. Yet the opposite side, the one we don't really get to see with our own eyes, but that we have pictures of from various missions, is exceptionally different. It does not have anything in terms of volcanoes. And the lack of volcanoes here and the huge presence of volcanoes here has been explained previously as the result of tidal activity from our planet and also as a result of various materials surfacing over time and heating up the surface of the side closer to us while leaving the other side completely intact. And so whatever is happening on the surface of the planet LHS 3844b might be extremely similar to the moon in the past, and this is of course due to the tidal effects from its star, combined with the fact that it also has extremely hot surface on one side and very cold surface on the other side. And also, just like the moon, it doesn't really have any atmosphere, which overall makes this object extremely interesting for some of the future studies. But until we have better telescopes to actually look at this object and to also see if there's any volcanic outgassing like you see right here that we can possibly detect, or any other features such as actual illumination from the volcanoes, we're not really going to be able to know much more about this planet. Right now this is still based on computer and numerical simulations, and it's also based on phase curves which are not super accurate because this object is 48 light years away from us. But future studies and of course future observations might actually help us determine if this is indeed the second ever object discovered that does seem to have a lot of tectonic activity on the surface. Kind of similar to some of the other objects like, for example, Venus in the past, Moon in the past, Io in present, and of course planet Earth, which at least for now is the only object we know of that has extremely active tectonic activity, which is also responsible for preserving the biosphere of planet Earth. And so finding other planets where tectonic activity is going on is extremely important. But more important right now is for us to find better techniques to essentially learn how to identify if these planets are tectonically active. If they do have volcanoes and of course plate tectonics, those planets are going to be extremely interesting for future studies. And so hopefully, thanks to studies like this, we'll be able to identify future techniques that will help us find more of these planets. But I guess for now that's sort of all we know about this planet. It's definitely exciting to know that it probably has volcanoes and maybe even plate tectonics, and it might have also experienced something similar to our own moon, but I guess until future studies we're not going to know much more. In the last few years, we've discovered quite a lot of exciting and really interesting exoplanets out there, with certain star systems even possessing exoplanets that could potentially be habitable and maybe even have some sort of an extraterrestrial life on the surface. But as our techniques improve and as new instruments are being developed to see even more, we keep discovering even more exciting worlds out there. Hello wonderful person, today we're going to be talking about yet another star system out there that has recently been discovered to have 5 exciting exoplanets, with one potentially habitable and one that seems to be approximately 1/2 of the mass of Venus, yet at the same time being the smallest planet discovered using a really exciting method. So let's talk a little bit more about this unusual star system known as L89-59 and find out what sort of planets we think they are as well. First of all, this is actually not the original discovery. The first time 3 of the planets were discovered was back in 2019. And back then, by using the TESS telescope, the original discoverers identified 3 potential candidates for what seemed to be exoplanets. It wasn't really confirmed right away, and the scientists were not certain what sort of planets they were, but the initial suggestions all suggested that they were actually terrestrial, relatively similar in size and in mass to planet Earth. But now, 2 years later, following more thorough analysis and investigations using a slightly different instrument, the scientists were able to establish relatively accurate measurements of mass, density, and also discovered 2 more exoplanets hiding somewhere in the star system, with one potentially habitable and being located right in the middle of the habitable zone as well. And now let's start right here. This is the image created by the European Southern Observatory. This is the solar system with Mercury, Venus, and Earth. And that's the star system we're talking about, L98-59. In this case, you're not actually looking at distances, but instead this diagram is scaled in order to make the habitable zones of the solar system and the other star system to match in the same region, with the rest of the picture showing us a kind of a temperature scale or a temperature gradient away from the star all the way to the end of the habitable zone. And since this is Mercury, it means that in L98-59 there are 2 planets that are even hotter than Mercury. But I think the most exciting part about this study is actually how they found these new planets and also what they used to analyze the original discovery as well. First of all, this is at a distance of about 35 light years away from planet Earth, so not too close, but also not really far away either. In order to perform a new analysis, the scientists from the European Southern Observatory use the most powerful spectroscopic instrument known as ESPRESSO that collects the light from the ESO's telescopes and then analyzes the changes in the frequency of light in order to see if the star itself is being pulled at by anything else. Okay, so it's actually easier to understand this if I show you a visual example here. So this right here is our sun, a copy of our sun. Right now it doesn't actually look like it's doing anything, and it doesn't look like there are any planets in its orbit. But once I zoom out, you notice there's a planet Earth, and it's orbiting in the same area where actual planet Earth orbits as well. But how can we possibly find it if there are no other signs for this planet, if there are no actual indications, no shadows showing, and no other way for us to see anything? Or in more scientific terms, it doesn't show us any transits, there are no shadows. Well, here we have a different method, and this is called radial velocity. This method works with a very simple principle. Because the planet and the star both contain mass, they actually end up sort of dancing around one another. Obviously, the planet being less massive moves a lot more, but the star is also sort of wobbling around a central point. Now for the solar system, our Jupiter does most of the pulling. It actually moves the sun by quite a lot. But even our tiny planet Earth has a bit of an influence on the sun. It shifts it just enough that if you were to have a powerful instrument, you would be able to find it. And that's precisely what ESPRESSO does. It looks for these tiny wobbles, and it finds those wobbles by looking at redshift and blueshift effects coming from the star. And so once again, if you look at the simulation from NASA here, notice how as the planet moves around the star, it either blueshifts or redshifts the light from the star. It's not a very dramatic effect, but if you have a powerful instrument, you can actually see this, and it's going to be periodic, and it's going to be detectable using modern methods. Here we're talking about changes in just a few hertz of frequency. Okay, so going back to our sun here, if I were to show you what's happening to the velocity of our sun by actually using the frequency change observations from the sun, it would sort of look like this. Every once in a while, specifically every 365 days, the velocity of the sun would change by about 18 centimeters per second. And that's because the Earth is pulling at the Sun and is making the Sun wobble just a little bit. And so that's kind of what the scientists in this paper did and analyzed the frequencies coming from this particular star system, eventually realizing that certain frequency changes seem to have a period coinciding with a potential planet orbiting in the region. And because 3 of these planets have already been detected using another method, they were able to confirm the existence of these 3 planets, but also discovered the mass of these planets, which allowed them to discover the density, and then discovered 2 more potential candidates. And so here the analysis suggested that the nearest planet seems to be about half the mass of Venus, approximately 0.4 masses of planet Earth. But because this planet is so close to the parent star, it's also probably kind of hot here. Nevertheless, this is definitely a rocky planet. The second object, which originally was thought to be some sort of a Neptune-like object, is also very likely a terrestrial world, a somewhat hot terrestrial world. And with a mass of about 1.4 masses of planet Earth, this is also a pretty exciting object that they were able to discover. The third object, which is a lot cooler in this case, is also pretty massive. It's about 1.5 masses of planet Earth, but for some reason it also seems to be a lot less dense. In this case, the scientists think that it's because it's an ocean world. It probably contains about 30% of mass as water. But because of its location in the star system, it's really unknown what sort of conditions this water is in. It could be just a really large steamy planet because it's actually pretty hot here, or maybe it's extremely hot and steamy on one side, but actually has a liquid ocean on the other side. So this could also be an extremely interesting object that they discovered. Here's the artistic representation of what this world might sort of look like. Although obviously it's not clear if it's actually blue like you see right here, or if it even has water on the surface. But then they found 2 more planets, potential candidates, slightly farther away, but in the area that's more habitable. Neither one of these planets transits in front of the star, so it would actually be impossible to see their shadows or to study their atmospheres, but they do seem to be there based on the observations from Espresso. So this one here is roughly around 3 masses of planet Earth, and it orbits around the parent star every 12.8 days. Now this might sound like it's really fast, but because this is a red dwarf, things here happen a lot faster as well, and this is why the planets are so much closer too. The star itself is about 3 times lighter in terms of mass than our own Sun. It's about 0.32 masses of the Sun. But it's really this last detection that seems to be the most interesting. First of all, because it's pretty much in the middle of the habitable zone, with the average year being about 23 days in length. But also because it does seem to be terrestrial, with a mass of about 2.4 masses of planet Earth. And depending on the atmosphere and a lot of other conditions, this planet has a huge chance of having actual terrestrial conditions on the surface. But unfortunately, since it does not pass in front of a star, we're not going to be able to study its atmosphere until some of the other techniques come out, or some other advances in telescopes or new instruments. So for now we can only really estimate the mass of the planet. We're not going to know what else is going on here. Nevertheless, it's still pretty exciting to discover yet another multiplanetary star system in a relatively close neighborhood, about 35 light years away from planet Earth. And because there are 5 planets here, with all 5 maybe even terrestrial planets, this of course makes it one of the most exciting star systems discovered in the last few years. More importantly though, it allowed the scientists to really push Espresso to its limits. For the first time ever, they were able to confirm an actual relatively small in mass planet by using the radial velocity method. And in this case, the planet was only about half the mass of Venus. This is the smallest planet to have ever been discovered using this method, or I guess in this case rediscovered, or confirmed. Unlike the example that I showed you with our Sun and planet Earth, where the actual change in velocity is about 18 centimeters per second, planet B was actually changing the velocity of the star by approximately 46 centimeters per second, essentially making this the record as of today. But we know that Espresso can actually see even smaller planets, or even less massive planets. Its limit currently is about 10 centimeters per second, which means that at least hypothetically, if Espresso-like instrument was looking at planet Earth, it would definitely be able to detect it orbiting around the Sun. Which of course also means that we're going to be discovering more of these planets, with possibly even smaller objects out there in some of the future studies. Hello wonderful person, this is Anton, and today we're going to be talking about ancient planets. Actually, oldest planets in the galaxy. And specifically, we're going to be talking about the new discovery coming out of NASA and out of TESS telescope, the discovery of a planet known as TESS 561b, which seems to be one of the oldest terrestrial planets we've ever found, which also raises a few mysteries that we currently can't answer. But before we talk about those mysteries, let's also talk about other planets we've found in the last few years. Starting with, I think, the most famous planet, known as the Methuselah planet, named after Methuselah, who I believe was a biblical character known to have a very, very long life. This planet, however, has him beat by a few billion years. This beautiful Jupiter-like object, this gas giant known as PSR B1620-26b, is an exoplanet roughly around 12,000 light-years away from us, located in the middle of a very large and very well-known globular cluster. And because we can estimate the age of a globular cluster relatively easily, and because we also normally think that a lot of stars in globular clusters appear at the same time, we believe that all of the stars here have very similar age. And in this case, we think that it's about 12.7 billion years. But unlike a typical planet, this particular planet also has a very strange star. It actually orbits a neutron star, in this case a pulsar. And to make things a little bit more interesting, the star system also has another star, a white dwarf, in orbit around the neutron star. So essentially, apart from being the oldest planet we found so far, the Methuselah planet also has two different stars that it orbits, one of them being a white dwarf and one of them being a neutron star. So it does have a lot of records. But this is a gas giant, so in that sense it's not as interesting as discovering a terrestrial planet. And finding ancient terrestrial planets has actually been very challenging. As a matter of fact, most scientists believe that finding ancient terrestrial planets would be practically impossible. But in 2015 we've discovered one such unusual star system known as Kepler 444 that has 5 different terrestrial planets with an average age of close to about 11 billion years old. Now this system was extremely unusual, especially because a lot of the planets here were in a relatively close orbit to the parent star, and also because this star itself was not that different from the Sun itself. This was a K-type star with a mass of about 80% of the mass of the Sun. Discovering such a system was very unexpected. And so finding such an ancient star system, especially not very far away from us, only about 120 light years away from planet Earth, was not something a lot of scientists expected, and it was definitely kind of unusual. But then for pretty much 5 to 6 years now, we haven't really found anything else so strange and so ancient. And that's of course until very recently, when the scientists were able to use the TESS telescope to identify yet another strange, ancient terrestrial planet somewhere out there. At a distance of about 280 light years away from us, this is sort of what the system looks like, with the star itself being extremely similar to our own Sun. This is a G-type star. Because it's over 10 billion years old, it means that this is almost the end of this particular star system. This star is soon going to reach the stage when it's going to start expanding and will definitely swallow all of these planets. But the planet of interest is this one right here. This is what NASA believes it might look like on the surface. It's currently known as TOI 561b, and here's sort of what it looks like compared to planet Earth. It's about 1.5 times the size, but surprisingly has an almost exactly the same density as planet Earth, which of course suggests that its composition is extremely similar to what we have here as well, although it is possible that it's slightly different and maybe has some other dense materials inside of it. But the major difference here is of course the distance to the star itself. Here a single orbit takes about 0.4 days. Which also means that the temperatures on the surface are ridiculously high, probably around 2500 degrees Kelvin, which sort of makes it the same temperature as on the surface of some smaller stars. And to give you a much better visual analogy of what this might look like, it probably looks something like this. It's literally a lava world with one side always facing the star and the other side always being in the dark. We don't really know what happens on the surface, but we do know that these extreme conditions also create some unusual atmospheres on the surface. For now we don't really know what this atmosphere is just yet, we just know that it's very different from anything we can imagine. And just like in the Kepler 444 system, there are at least 2 more planets here that are potentially terrestrial, although maybe also something known as the super-Earth, and 2 planets that seem to be Neptune-like, which would probably make them look something like this, Or maybe something like this. This is according to some of the NASA simulations. But as you can see from this simulation, these unusual 5 planets all orbit extremely close to the star, within the orbit of Mercury, which of course implies that in a few 100 million years, when the star starts expanding, all of these planets are going to be gone forever. But the most important discovery coming out of these star systems is not that they're old, but that the universe was creating these terrestrial planets for billions of years. Nobody actually expected we would find such ancient terrestrial planets somewhere out there, and especially ones with composition and density similar to planet Earth. This means that these planets, terrestrial planets, may exist and also remain stable for billions of years, which is great news for those scientists that are searching for extraterrestrial life somewhere out there, or that are searching for some other planets similar to planet Earth. These discoveries imply that many different ancient terrestrial planets exist out there, and some of them could have probably maintained conditions that we would call habitable for a very long time. Now obviously it's none of these planets are just too hot and too close to the parent star, but discovering these planets definitely helps us in our search. But one of the more unusual mysteries about this planet right here, the closest planet to the star, is its high density. Because these planets are so ancient and because they were created a long time ago, we would expect the stars where these planets are located, along with the material that these planets are made from, to be relatively low in metals, in materials that are not hydrogen and not helium. And because of this, we expect them to have relatively low density. And most of the planets that are usually discovered that have billions of years of existence normally have really low density and for the most part are made out of materials that are hydrogen, helium, and materials that are lighter. They don't usually contain a lot of iron, they don't usually contain a lot of nickel or other stuff that makes terrestrial planets dense and that gives them a lot of mass. But in this case, because this strange hot planet seems to contain relatively similar density and not really that different of a mass and size compared to planet Earth, this suggests that it has a lot of metallic materials inside of it. And that sort of contradicts some of the theories and predictions from these early planetary formation theories. As a matter of fact, theoretically, nobody expected we would even find these ancient rocky planets that have aged over 10 billion years old. But we found at least 2 star systems that have them, and there are several terrestrial rocky planets in each of these systems. And that currently has no good explanation. And so here the only explanation is that either there are some really major exceptions to the rule here, with certain stars and certain planets in the early universe being able to have a lot of these metals and a lot of these materials that would create a terrestrial Earth-like planet, or we might have a mistake somewhere when it comes to the theories and the ideas of planetary formation in the early universe. Either way though, these are exciting discoveries and will definitely help us understand how such unusual planets similar to planet Earth could have been formed to begin with. More importantly though, it will also help us understand how these planets evolve over time, and in some sense will also kind of guide us in trying to understand how the solar system will evolve and what one day might happen to planet Earth and other terrestrial planets like Mars and Venus in our own solar system as well. Hello wonderful person, this is Anton, and welcome to this imaginary version of Tatooine. Well, mostly because I can't really use the real version because I'm sure Disney is not going to like that very much, but also because this wonderful person by the name of Michael Tynior created this really cool free software simply known as Tatooine that basically recreates this iconic scene from Tatooine with the beautiful 2 stars in the night skies. Now by now this scene is more or less iconic, and I think most people today are quite familiar with the fact that Tatooine has 2 stars. And because of this, even astronomers today started referring to these hypothetical planets around 2 stars as Tatooine worlds, or Tatooine-likes, or basically Tatooines. And a lot of scientists today are actually trying to solve the mystery of whether these worlds truly exist. And the reason why it's a mystery, and the reason why nobody really knows if they truly exist is, well, it's actually really simple. It's very easy for a star to hold on to planets when it's just one star in there and not a lot of other gravitational interactions. Like for example, unless there's a massive object like a brown dwarf, it's usually going to be able to hold on to most planets pretty easily. Although even in our own solar system, objects like Jupiter affect other planets and affect the star itself to the point where it becomes quite visible. Our Sun, for example, because of Jupiter, even has its own orbit slightly shifted as Jupiter moves around it. But today we know that most stars out there, actually possibly even like 3/4 of all of the stars, are binary. There are usually two stars, and for the most part, most stars in our galaxy have partners. Now, because there are two stars, there are now two gravitational objects, and so it's a lot more difficult for an object to maintain a stable orbit around these stars. Alright, let me help you visualize this. So let's just say I place a random Earth-like object in the orbit of these two stars. This is a binary system, and I'm just going to smack Earth right here. All of this is most likely going to destabilize its orbit, and essentially most of these Earths, most of these planets, are not going to be able to maintain orbits around these two stars. One of the Earths just collided. And that's because this is a binary system where the gravitational interaction and gravitational stability points are actually constantly changing and are very, very different. Now, it doesn't mean that these binary systems don't exist. They do exist, and they even have their own name, but also a really difficult mathematical formula related to those orbits. These are known as circumbinary planets. Circumbinary in this case meaning that they orbit both stars. Now, obviously having an orbit around one of these stars is also possible, and that's actually the most likely scenario here, and in this case the orbit is going to be stable. But having an orbit around two stars is a lot more challenging, but not impossible. And there's actually a region around these two stars where you can still have a pretty stable orbit. For example, here is one of many possible orbits, with the orbit itself being a little bit more eccentric than usual. And we've discovered over the years quite a lot of these different objects that seem to possess these types of planets. Interestingly, one of the first discovered exoplanets that was discovered back in 1993 was actually a circumbinary planet around a white dwarf and a pulsar. But there are not a lot of them, and they are quite interesting to scientists, mostly because, well, it's difficult to imagine how these planets form stable orbits around the stars that do actually produce a lot of instability. Now, this is actually one such system discovered by the Kepler telescope. This is the system known as Kepler-16. This is probably one of the more well-known circumbinary planets. And in this case, it's an object that's somewhat similar to Jupiter, but about maybe 30% the total mass of Jupiter. So it's definitely possible for these planets to form naturally. Another good example here is from this interesting system known as Kepler-64, also known as Planet Hunter 1 system, because it was actually discovered by citizen scientists. It was the first planet discovered by citizen scientists, so it's known as PH1. And in this case, this is in a quadruple star system, where the planet itself orbits a binary star system, and the binary star system then orbits another binary star system, making this a very odd and very unusual system, but an actual system nevertheless. And today we even have some really impressive observations from some of the early planetary systems, where the stars themselves are just being born and the planets haven't even formed yet. So for example, here's a circumbinary disk around AK Scorpii, a young star system in the constellation of Scorpius, and this image shows us the ring that will probably become either one or possibly even several planets. But this ring is actually extremely small, it's very thin, at least compared to a typical planetary ring. And so this actually helps us visualize where these stable orbits are. But a much more important question is, of course, well, in regards to this, to Tatooine. Can a habitable planet exist around a binary star system? Or just to rephrase this, can we have a circumbinary habitable planet? And that is the question that the scientists in the study that you can find in the description below decided to investigate, analyze, and mathematically answer. And the short answer is yes, and they even might have found at least one really good candidate. But what's even more unusual about all of these star systems they looked at and analyzed is that they also all possess a relatively massive Jupiter-like object somewhere in its orbit. And so if I were to replace our hypothetical Earth with Jupiter here, well, first of all, it would actually create quite a lot of instability in the system because its mass is much higher. It might even shift the orbits of these two stars. But then eventually they will probably reach some sort of a balance. This, however, will make creation of any other planet in the system extremely challenging. But as the scientists discovered in the study, not impossible. And it seems that it's even possible to have a habitable zone in the system. And so even in the presence of giant massive planets, it looks like there is a chance for certain planets to still exist and still stay habitable. Now, even though Kepler telescope was operational for several years and discovered several thousand different planets around different types of stars, it actually only discovered 12 circumbinary planets, which means that they're either extremely difficult to find or more likely just very, very rare. But pretty much all of these circumbinary planets found by the telescope are, first of all, really massive. They're usually at least the mass of Neptune, so about 20 masses of Earth, but they're also really far away, over 2,000 light years away. So trying to find another terrestrial world in these systems is kind of difficult right now. Until we get better telescopes, we're not going to be sure if there's anything else here. But because there are so many chances for instability from the other planet or even from one of the stars, generally speaking, the conditions for habitability here would be quite hostile. And mostly because of the amount of perturbations that will still be created by the stars. It means that sometimes this planet is going to be really close to both of the stars and thus be much hotter. Sometimes it'll be really far away and much colder, so it's going to be very difficult to have stable conditions on these planets. At the same time, having several massive planets in the system will destabilize this even more. So if there's already a massive Jupiter-like object, it does have a very high chance of perturbing other planets just enough to make them not so habitable. And so in this paper, the scientists took all of this into consideration. They considered the fact that there could be strange, unusual massive objects here. They looked at the class, the mass, luminosity, spectral energy. They also considered gravitational effects from other objects nearby, and a lot of other parameters that normally affect the orbits of planets. And by plugging all of this into various equations, while also considering something they refer to as climate inertia, or basically how fast the climate would change depending on the location in the star system, they did realize that the habitable zones are definitely possible. And so after doing the analysis, the scientists in this paper established that of all of the circumbinary star systems they analyzed, most of them still have a pretty high chance of having some sort of a habitable world, or at least habitable zones. But there are a couple of them that don't actually have a very high chance. Like for example, this one right here, Kepler 1661, has a planet that's a little bit too massive, so the habitable zone, if it exists, is probably really small. The planet just destabilizes the system too much, with the biggest habitable zones being around Kepler 35 and Kepler 38. But the best system, the most likely system to have the largest habitable zone and thus potentially terrestrial planets, is a system known as Kepler 38 that's surprisingly pretty far away from us. It's about 3,800 light years away. But because of the overall structure of this system, the chance for a habitable zone that's stable is really high here. Thus suggesting that one day we could maybe really discover a true world that's kind of like Tatooine. An actual world with two stars, or in some sense binary sunset and binary sunrise. Something that we've been kind of imagining for the past 40 years since the original Star Wars came out. But overall, this paper does suggest that pretty much most of these circumbinary star systems do have some sort of a habitable zone that extends to roughly around 2 astronomical units away from the center. After this it becomes too unstable, and if you're too close to the star system, unfortunately it's too close to the star to be habitable. But because generally speaking it's a little bit more difficult to detect a planet around 2 stars compared to a planet that orbits a single star, it might take a little bit longer for the scientists to finally discover a terrestrial world around a binary system. Hello wonderful person, this is Anton, and today we're going to be talking about the most populous stars in our galaxy, known as red dwarfs. And more specifically, we're going to try to answer the question, can anything actually survive in these star systems? Can any life prosper here? And hypothetically, can life actually produce oxygen? So the question we're going to try to answer is, can photosynthesis occur around red dwarfs? And all of this is based on a relatively recent study that you can, as always, find in the description below, that performed a really interesting analysis of whether certain bacteria can survive in simulated conditions similar to the conditions we would find around a typical red dwarf star. And so in this case, the only purpose of the study was to see if photosynthesis, one of the most important chemical reactions on the planet, can hypothetically occur around a typical red dwarf, or if it's something that we shouldn't even try to look for because it's impossible both chemically and of course physically. And this question is of course really important because most of our knowledge of life is from our own star system, from the star system known as Well, the solar system, of course, and the star here is what's known as G-type star, but they're not actually that common. The most common type of a star is this one right here, a typical red dwarf. And moreover, all of the most exciting discoveries of different exoplanets so far, including all of the exoplanets we're discovering right now, the vast majority of them are actually around red dwarfs. Including the most exciting discovery of the nearest star system, Proxima Centauri, and the 2 planets, with one Proxima b being located in the region where we kind of expect liquid water to exist, in the so-called habitable zone. And with all of these other red dwarf systems out there, including the famous TRAPPIST-1 system, it's kind of important for us to understand if life can hypothetically exist here. Obviously, we want to know if life could have developed here naturally, but also if one day we become some sort of a species that learns how to travel across stars and learns how to colonize other star systems, we would want to find out if being able to establish a functioning colony here is a possibility. Can plants grow here? Can we, for example, establish a farm on the brighter side of this planet and use the stellar light for photosynthesis? Because we know, for example, that red dwarfs actually produce a lot less optical light, and as you can see also a lot of flares, and they also don't produce as much light that's usually required by plants. And so even though these stars are really bright in the infrared, they're very dim in the optical frequency of light, and of all of the frequencies, they seem to mostly produce red light. And to try to explain to you why this is a very intriguing question, let's take a look at the difference between a typical red dwarf and our own sun. In this simulation you can kind of see the size differences, but what's not apparent here is the difference in luminosity or the amount and types of light produced. Here, unfortunately, the red dwarf does seem like a pretty bright star as well. But you can see the more realistic radiance, or spectral radiance in this case, in this graph. Notice how a star like our sun mostly produces visible light and also has a relatively high spectral radiance for this light. And these are the frequencies that are normally used by various plants and also various algae during chemical reactions like photosynthesis. But a much cooler star, such as a typical red dwarf, will only have a very tiny amount of light as red light, with only some light being yellow, and the vast majority of it is going to be in infrared or even longer wavelengths, with the total radiance being much lower as well. So not only do red dwarfs have mostly red light, they also seem to have very low amounts of light to begin with, meaning that all of the planets here will be extremely dim, and any potential life on the surface will mostly be receiving a lot of red light. Well, actually no, some red light, not a lot of it at all. But these amounts are so minuscule that it's important to know if anything can possibly survive here. And this is why this experiment and this particular study are so interesting, because they were able to create these artificial conditions that we would expect around a typical red dwarf. And they were then able to test these conditions scientifically by varying certain parameters and also by using certain organisms that we know can exist in these extreme conditions. Which also, by the way, includes extreme radiation and potential flare conditions that we can usually find around a typical red dwarf. And by the way, completely unrelated to all of this, and this is more of a sci-fi slash geeky fact, but you know how eyes on Earth evolved to see things in the optical light? And we know that in the Predator series, Predator for the most part sees the infrared light as their main source. So it's totally natural to assume here that Predator as a species came from some sort of a red dwarf star somewhere nearby. Which also scientifically makes sense, because any life evolving around red dwarfs would most likely develop an ability to see in the infrared, not so much optical light. Anyway, getting off track, back to reality, photosynthesis, and possible life on other planets. Let's start with this map right here. This is actually a map of photosynthesis on planet Earth. Here on land you can see that the dark green, that's essentially the various amounts of chlorophyll on the surface of the planet, with very little here in the Sahara Desert, a lot here in the sub-Saharan regions. But notice how in the waters we also have quite a lot of various hotspots, especially one right here, and also a few right here in the Arctic, some right here, and of course one in the Black Sea and one in the Caspian Sea, that also have very high concentrations of chlorophyll and thus the ability to produce oxygen on the planet, with really large amounts of oxygen coming from these regions in the oceans, and specifically oceanic phytoplankton, which usually resides in certain regions around the planet. But all of the life on planet Earth requires light to be of certain frequency, specifically between 400 nanometers and 700 nanometers. or in other words between violet light and red light. Anything lower than that in wavelength becomes ultraviolet, and that's actually slightly more dangerous to life because it starts breaking up the cells themselves. But anything longer than that becomes infrared, and infrared just doesn't have enough energy for most of the life on the planet. But in the last few years, scientists have discovered a lot of different specific extremophiles, and here we're talking about cyanobacteria extremophiles, that do actually survive on light that is in infrared. And here we're talking about light that's about 750 nanometers in wavelength. These strange bacteria found a way to survive and to thrive in conditions where no other bacteria can survive because, well, it's not enough energy for them to create necessary chemicals and to initiate photosynthesis. And naturally, the next step was to put these bacteria into these experimental conditions and then see if the bacteria could reproduce, survive, and photosynthesize for up to 240 hours. To make this a little bit more scientific, they actually chose 3 conditions. One was very similar to the starlight that our sun produces, one was similar to a typical red dwarf, and the last one was just that infrared light that's about 750 nanometers in wavelength. And I guess not surprisingly, all of the bacteria used in this study were able to survive and thrive in the conditions similar to a typical red dwarf. But a lot of these bacteria were not actually able to grow with just that far red light, mostly because they're not able to photosynthesize and to produce other types of chlorophyll in certain conditions. In other words, these bacteria were actually using some of the available light, such as orange and yellow light, that is also available around red dwarfs. But at least 2 bacteria were to some extent successful even with that little amount of red light, meaning that even in the extreme conditions where mostly the red light is produced by a red dwarf, we should still expect at least some types of photosynthesis to be possible. And so what does all of this mean? Let's jump onto the hypothetical surface of a TRAPPIST-1 planet and briefly talk about the implications. So this is what it might actually look like on the surface here. Now, if we have water, or hypothetical water, and if we have a star that produces predominantly red, infrared, and some yellow light, we might be able to discover certain bacteria and certain algae here that has adapted to basically use these conditions to produce oxygen and to produce other atmospheric conditions that could be necessary for other types of life to develop. And because we're talking about extremophiles here that are able to survive very hot conditions and even high radiation, they could also hypothetically survive very powerful flares coming from these red dwarfs as well. And because photosynthesis is now theoretically possible and because life can hypothetically survive here, the next step would be to start looking for the signs of oxygen coming from the surfaces, from the atmospheres of these distant planets, such as the planets in the TRAPPIST-1 system. But obviously just seeing signs of oxygen might not really be a good proof that some kind of a vegetation or some kind of a bacteria live on the surface of this particular planet. We know that oxygen can be produced through other chemical means. There is, however, a very interesting technique that could be used by the upcoming missions such as the James Webb Telescope that is already used here on Earth to determine, for example, the health conditions of various forests on planet Earth. So the way we study this today is using the phenomenon known as the red edge. Red edge in this case being this edge right here at the end of the red light. And this interesting phenomenon applies to all of the vegetation on the planet. When a typical leaf starts absorbing light from the sun, it actually ends up absorbing most of the optical light, including all of the colors of the rainbow, and some of the higher frequencies such as ultraviolet light, either goes through the leaf or gets to interact with some of the structures, potentially damaging them. But the infrared light surprisingly gets reflected by the structures inside the leaf. And because of this, if you were to look at a typical tree or really any vegetation in the infrared light, you would see this extremely bright, extremely oversaturated object, which is exceptionally easy to see from outer space as well. All of the trees and all of the vegetation basically create this very interesting reflective infrared and also very saturated picture that is visible from a very far away distance. And so naturally, if we were to see something similar coming from another planet, this unusual reflectivity and unusual appearance of a red edge on another planet, the only natural explanation here is that something is creating similar structures to a typical leaf or a typical tree on another planet. But in case of red dwarf planets, we would expect this red edge to be maybe slightly farther toward the infrared, maybe around 750, maybe even 800 nanometers. So basically slightly shifted to the right on this picture right here. And detecting something like this from, for example, Proxima Centauri, which can totally be done by James Webb Telescope in the next few years, would only mean that we've just found the possible signs of vast amounts of algae, trees, or some other strange life that's producing these effects and is also producing a lot of oxygen on these distant planets. And if by some luck we actually do find this on Proxima b, which is of course the nearest red dwarf planet to us, this means that this probably exists around the majority of planets out there, simply statistically speaking. If, however, we don't find anything, well, that's kind of expected right now. Statistically, we don't think we'll find anything here. But once again, this is only something we're going to know in the future once better telescopes are available to us and once we're able to observe these things in the infrared with much higher resolution and, of course, much better visibility. For now, we can only speculate and can possibly do experiments, such as of course the brilliant experiment I mentioned in this video, that you can read more about in the paper in the description below. Until we discover something else or until another really cool experiment, that's pretty much all I wanted to mention in this video. And because of this, I'm always fascinated to talk about this idea of astrobiology or life outside of planet Earth. Hello wonderful person, this is Anton, and today we're going to be talking about a discovery of a potential planet, possibly even in the habitable zone, around one of the most exciting star systems next to us. The system currently known as Rigel Kentaurus and Ptolemy, although that's not a name that a lot of us have heard of before. These two stars are more commonly known as Alpha Centauri, and that's probably the name that I'm going to be using for the rest of the video because the other two names are kind of confusing. Now, I'm sure you have heard of these stars before because that's basically the closest star system to us. The system of Alpha Centauri is technically actually connected to the neighbor Proxima Centauri, which can be barely made out right here where the circle is located. And together Alpha Centauri stars and Proxima Centauri form this somewhat interesting union, with Alpha Centauri A and Alpha Centauri B orbiting around one another every 79.9 years, with the average distance between these two stars being equivalent to the distance from the Sun to Uranus, roughly around 18 astronomical units. Whereas Proxima Centauri is much farther away at about 13,000 astronomical units, or about 0.2 light years away. And though mostly we've talked about Proxima Centauri so far because we've already confirmed two planets here, with one being in the habitable zone of the star itself, the scientists have always been more excited about trying to find something in the Alpha Centauri, because being the closest star system to us, it's also the closest star system with the stars very similar to our Sun, so-called solar analogs. The stars that are not too active, that don't really produce a lot of flares, and the stars that are generally mild enough to provide necessary conditions for long-term habitability of different planets. And here is a picture that sort of demonstrates how these stars compare. We have the Sun, we have the larger Alpha Centauri A, or the Rigel Kentaurus as it's known, with a mass of about 1.1 masses of the Sun, and the luminosity that's about 50% higher than the Sun. Then we have the slightly smaller Ptolemy, with the size of about 0.9 masses of the Sun, and only about half the luminosity of the Sun, and lastly we have the Proxima Centauri, a typical M-type dwarf. And though Proxima Centauri is smaller, it's also a lot more active and produces a lot more extremely powerful flares, many of which have been detected in the last few years. And so naturally discovering something around the Sun-like stars is way more exciting, which is why in the last few years there have been a few announcements of possible planets. One of the first announcements was back in 2012, but within 3 years, several studies confirmed that it was nothing but the noise in the data. The planet most likely did not exist. Then, only a year later, the scientists observed an unusual passage of another possible planet. This was basically a shadow of a planet passing in front of a star, which did suggest that there could be an object orbiting one of the stars here. Now this hasn't of course been confirmed yet, but if confirmed this would be a really tight planet orbiting the Alpha Centauri b, also known as Ptolemy. And surprisingly this was an object with a total size of about 94 size of planet Earth, but the orbit here would be really close to the parent star. A single orbit here only takes about 20 days. This implies that this would be some sort of a lava world, This of course has never been confirmed since, and it's been over 7 or actually 8 years now, and this means that it could also have been a false detection. Many of these have happened in the past, so this wouldn't really be the first. But because this is such an exciting star system and because this is our neighbor, this has not stopped scientists in trying to discover more potential planets. And the most recent analysis has actually used something very different, something that has never really been used in such a way, and something that potentially discovered another planet, and this time maybe in the habitable zone of the star system. Now, because this is our neighbor and because the star is pretty bright in the night skies, this actually creates a lot of problems for certain techniques in trying to detect planets around it. But there is one technique that we can definitely use on this star system, something that has also been used in the solar system quite a lot with our own sun. The method that's sometimes known as thermal chronography. It's essentially when you block the central object, in this case it's the sun, and then try to look for certain other objects, bright and possibly hot objects, in the vicinity. This is normally how we look at comets approaching the sun, and this is normally how we also discover certain objects, such as this one right here once again, that are both really close to the sun and also produce a lot of heat that's otherwise invisible because the sun is really bright and essentially overshadows their heat. And so if we block a star and then look at it in infrared imaging, for example, we can actually see heat generated around the star system. And because we know that planets and pretty much all objects do produce heat simply by reflecting or even through generation of heat on the inside, we can usually see them assuming that nothing blocks their heat or their emissions. And back in 2019, the famous Breakthrough Listen, or in this case one of the breakthrough initiatives known as Breakthrough Watch, began its collaboration with the European Southern Observatory and allowed the scientists to use a new tool known as VISIR, which stands for Very Large Telescope Infrared Imager. You can learn more about this particular tool in the article in the description below. And this allowed the scientists to now directly image some of the nearby stars, specifically stars within about 20 light years away from us, and to look at their infrared signatures. The main purpose, of course, being discovering new planets. Now, after about a year and a half, we now have one of the most exciting reports, a planet in the habitable zone from the closest star system to us. The planet that's visible in this image right here as this relatively large heat spot in the image produced by the VISIR tool. Now remember, this is still a preliminary discovery, but if this is confirmed and if this is indeed a planet orbiting in the star system, this would be a planet similar in mass to Neptune and would actually be right in the middle of the habitable zone, meaning that it would have conditions necessary for liquid water to exist. But it's also important to know here that a lot of other artifacts were discovered in these images, some which you can see in the image where the arrows are pointing, which obviously suggests that this is not a conclusive result just yet, and there could be a lot of interpretations to what it is that we're looking at here. Specifically, the spot that's referred to as C1 or Candidate 1 could also be cosmic dust, or really hot cosmic dust. It can also be some sort of reflection based on something else in the background, or for all we know, it could also be a distant object just in the right location where the scientists were looking at. In other words, it doesn't actually confirm yet that this is a planet, but there is a way to confirm this. If we look at the star again in the next few days or possibly the next few months, and if we discover that this object shifted a little bit and is definitely orbiting something, we know for a fact that this is probably a planet. Because so far this is actually only based on 100 hours of observations. We'll need to do a lot more observations possibly in the next few months to see if this is really there. But also based on the amount of heat detected coming from this object, it most likely is not some sort of a terrestrial planet, and instead is more likely to be some sort of a gas planet, possibly even a gas giant. Although if it is some sort of a massive planet, it's more likely we would have found it a long time ago, because normally we can see these massive objects because of their effects on the star. They normally shift the star's motion across the night skies quite a lot. Because we haven't seen anything like this from Alpha Centauri, this planet is probably a lot less massive. But it still doesn't mean that it's a terrestrial planet. Because as of now, it does seem like the planet is reflecting a lot of the heat from the star, which of course suggests that it's probably larger than planet Earth and seems to be emitting a lot of heat as well. But more importantly, this is a huge milestone for the project itself. It only began operating a year and a half ago, and it's already collected a lot of useful data and has potentially discovered a habitable planet in a nearby star system. And of course, if confirmed, this would be one of the most exciting discoveries of the last few years. Which of course would also make the Alpha Centauri and the Proxima Centauri systems as essentially some of the most interesting systems in the vicinity. It would mean that both of them contain planets in the habitable zone, which at least statistically speaking would mean that pretty much most of the stars out there would have something in their habitable zones as well. But it's also important to remember that we've always wanted to find planets around binary systems, mostly because we want to learn and we want to understand how these planets survive for billions of years. It's generally really hard for stable orbits to form in binary systems, and for example for both stars here, these stable orbits are only within about 2.8 astronomical units, with the habitable zone for the smaller star being within 1.3 astronomical units, for the larger star almost reaching that limit at 2.2 astronomical units. This of course implies that if this particular planet exists in the star system, it's basically sort of already at the limit of where a stable orbit can form in the star system. If it's a little bit farther away, or if its orbit is eccentric, it does have a high chance of suddenly getting kicked out of the star system and basically becoming a rogue planet or colliding with the stars. And so once again, if this particular planet is confirmed and if it truly exists out there, this would be one of the most exciting and possibly one of the luckiest discoveries we've made in the last decade. A very strange, a very unusual, and a very peculiar object that really shouldn't actually even exist, but seems to exist nevertheless. But it will take a few months to confirm all of this, and possibly even longer. So for now, we don't really know if it's truly there, or if it's some warm dust, or possibly some other reflection coming from the star that was maybe formed by some sort of a cometary tail or some other activity. Not so different, of course, from what we're seeing right here when the comet passes really close to the sun itself. So definitely exciting, but we just have to wait and see what happens with this. Hello wonderful person, this is Anton, and today we're going to be talking about this really exciting planet that was discovered back in 2015 that also seems to be the only planet we know of that lost its original atmosphere and now has acquired its second atmosphere. And this planet, known as Gliese 1132b, is actually one of two objects in this particular star system, both being extremely interesting. But let's actually talk a little bit more about this because it's a pretty exciting discovery. So first of all, this planet, as I mentioned, was discovered around 6 years ago. And even back then, the scientists became really excited because of the location of the planet and also because of the star and the distance to the star. This is about 40 light years away from us, so it's close enough for us to actually be able to study its atmosphere and a lot of other features. Also, the way that this planet moves and crosses the star while producing the shadow allows us to produce very detailed observations of what's inside the planet's atmosphere. When the planet was discovered, the scientists were convinced we're going to be able to see the atmosphere, to know exactly what the atmosphere is made out of, and even be able to tell the color of the night sky, or even be able to tell the color of sunsets on this particular planet. Mostly because, compared to our own solar system, this is actually a red dwarf star, so it's about 1/5 of the size of the Sun, and on top of this, the planet itself is much closer to the star as well. A single orbit here only takes about 1.6 days. So in some sense, this is a typical red dwarf system, but it's just perfectly located for us to study the atmosphere and to really learn a lot about this planet. But by looking at this planet, and of course by looking at the star for a long time, and also by doing a lot of other analysis, the scientists now estimate that the original atmosphere of this planet was most likely essentially hydrogen, kind of similar to what we have in planets like Saturn and Jupiter, which of course means that the original GJ1132b was probably a mini Neptune. Or in other words, it wasn't actually a terrestrial planet like you see right here, but it was probably more of some sort of a gas giant-like planet, although not really a gas giant, a mini Neptune. But with time, because of the proximity to the star, all of this heat started to evaporate the atmosphere, and all of the atmosphere was initially lost. Now, this is a concept we refer to as a Chtonian planet, a planet that evaporated and only a crust and the terrestrial core was left behind. This is actually something that the scientists believed for a pretty long time. All of the observations suggested that, but some of the recent observations, by looking at this location again, started to discover certain other elements present in the atmosphere of the planet, specifically things like methane and hydrogen cyanide, along with some parts of molecular hydrogen as well. And what this detection suggested is the fact that the planet must have created a second atmosphere after the first one was destroyed. Moreover, it seems to be able to recreate this atmosphere as more and more of it is lost. So some of this hydrogen that's still present there is still being lost to the rest of the star system, but the majority of new molecules formed that produce the atmosphere seem to be coming from within the planet itself, most likely either as a result of massive volcanism on the planet, or more likely through various seeping cracks around the planet where the gas just kind of leaks out through these various cracks formed on the planet, probably because of all of the tidal stress that the planet experiences as it orbits the star. With all of this hydrogen cyanide and methane very likely forming as a result of various gases mixing within the mantle of the planet, with hydrogen cyanide, for example, containing nitrogen, which is a very common gas present on planets like Earth and Mars, and both methane and hydrogen cyanide also containing hydrogen that was present on the planet initially. And though this planet is still pretty close to the star and is still experiencing the same amount of radiation and is thus losing some atmosphere even now, it probably reached some sort of a balance by now where the amount of hydrogen lost to the star system is sort of replenished through the emissions of all of this gas coming from within the planet itself. But the surprising calculations from the study also suggest that the atmospheric pressure here is extremely similar to the pressure of Earth. Basically, the amount of gas here is roughly around 1 atmospheric pressure, which means that it's kind of similar to Earth in some sense. So these calculations actually suggest that the atmospheric pressure here is roughly around 1 atmosphere. But unlike Earth though, the gases here are very different. As a matter of fact, here's the illustration produced by one of the artists. It's probably more a Venus-like world. The atmosphere is very hazy, it's also obviously somewhat toxic, and to some extent, somewhat resembles early Earth, more so than really anything else we have in the solar system today. Earth back in the days also was a hydrogen-dominated planet, with a lot of methane, carbon monoxide, and a lot of other components present in the atmosphere, making it somewhat toxic as well. But eventually, with time, Earth transformed into something a little bit more beautiful and turned into a water world, as I've discussed in one of the previous videos, somewhere right there. So anyway, back to the planet. Also, unlike Earth, this object is probably extremely hot, at least on the side of the planet that's facing the star. This planet is tidally locked, like a lot of other planets orbiting red dwarfs. But the question here is, of course, what happens in the twilight area, specifically area right here between the dark and the bright side of the planet, or what actually happens on the dark side of this planet. This is actually something that a lot of scientists would now love to know. And remember, because of the dark side here, the temperatures are going to be more bearable. Also, we have this very thick atmosphere with certain compounds that can technically be used by bacteria. Now, I was actually wondering what sort of temperatures could be produced on this planet, especially on the dark side, so I tried to create this simulation of this planet using Universe Sandbox. And more specifically, I really wanted to look at this temperature distribution graph that usually shows you what a typical tidally locked planet would have on its surface. So all of this red stuff here, that's super hot. This is like hundreds of degrees Kelvin, basically even hotter than Venus. And pretty much everything along the equator, assuming that the planet spins in the same direction as planet Earth, is still pretty hot, just over 200 degrees Celsius. But on the polar side, especially in certain locations, the temperature actually becomes somewhat bearable. As a matter of fact, right here, that's the average temperature of planet Earth. So the way that things are looking right now, what we have here is a really exciting planet. Even though it's tidally locked, that could actually provide it with certain locations on the surface, depending of course on how the atmosphere is distributed across the planet, which would allow it to have temperatures somewhat similar to planet Earth, but with those locations most likely being in complete darkness. So hypothetically, if there is any bacterial life here, it would most likely have to use some other power source to survive, very likely chemical source. But let's not go into this whole alien life discussion yet, because we don't really know what's happening on this planet. What we do know, however, is that this planet most likely undergoes a lot of tidal stress and a lot of tidal heating, which is a process that usually happens to certain moons or even certain planets when a more massive object starts to kind of stretch them apart. A very good example here would be the moon known as Io orbiting Jupiter, which is sort of being pulled at by Jupiter, but also by its partners Europa, Ganymede and Callisto. And because of this, the moon gets stretched into an egg and then returns back into a spherical shape. In contrast, our own moon is always an egg, Because of this, Io is the most volcanically active object in the solar system, and all of the stuff from inside Io comes out and creates a lot of different atmospheric effects and also interacts with Jupiter as well. So something similar very likely happens around this planet as well. And the reason for this is that it has a partner that orbits not so far away from this particular planet, the object known as GJ132c, and possibly even another partner even farther away. At the same time, a lot of these tidal effects are increased dramatically because of the orbit of the planet. The planet orbits with a slight eccentricity. And because of this, this planet very likely has extremely thin crust. So thin, as a matter of fact, that it probably has no hills, no mountains, basically extremely flat terrain. And all of this, of course, suggests that this is an extremely volcanically active planet. Or at least on one side. We don't really know what happens on the other side. For all we know, one of the sides here is extremely active and very hot, so sort of like this illustration I showed you previously, but the other side, the one always facing the darkness, has a somewhat more comfortable climate. That's of course not something we can prove or show just yet, but it's something we can technically simulate using some of the computer simulations we have today, like the NASA's Rocky 3D. I'm sure someone will come up with a study in some near future. Either way though, so far this is one of the most exciting discoveries of exoplanets out there, and definitely a pretty cool planet simply because of the fact that it has very similar atmospheric pressure to Earth and the other object in the solar system known as Titan. So now that means that we have three objects with pressures where technically you can kind of stand and not get crushed by anything, or lose consciousness because there's not enough pressure. Although on this particular planet, standing here without some sort of a gas mask, the hydrogen cyanide is probably going to get you pretty quick. Oh, and the other exciting fact that I forgot to mention is that the planet is also relatively similar age to planet Earth, about 4.5 billion years old. So, very exciting discovery, very exciting star system, and for all we know, we might also find something super exciting around its partner, which is actually also a potentially rocky world, slightly larger than planet Earth. And also slightly cooler in temperature as well, because its orbit is around 8 days around the star. And in this particular simulation, this is what it sort of looks like. It actually resembles Earth to a very eerie extent. Hello wonderful person, this is Anton, and today we're going to be talking about new analysis and new discoveries coming from one of the more exciting systems near us, the star system known as Tau Ceti. And though we talked about this star system a few years ago, it's actually worth talking about it again, because new discoveries suggest that it actually has some really interesting planets in it. Specifically, it seems to possess 8 different planets, with at least one of them potentially being in the habitable zone. But let's discuss this in a little bit more detail, starting with the star itself. The lonely star, approximately 12 light years away from us. If you remember the distances to other stars, this means that this is actually one of the closest stars to us. As a matter of fact, this is the second closest G-type star, and G-type stars are the ones we are particularly interested in, simply because this is what you would call a solar analog. It's a star extremely similar to our Sun, at least in terms of the amount of energy it produces. Here's, for example, how it compares to our own Sun, with the Sun being on the left. So it is a little bit smaller, it's about 78% of the total mass of the Sun. It also seems to produce about half of the luminosity of our Sun, but in terms of the age, it's relatively similar. It's about 5.8 billion years old, although it does seem to only contain about 1/3 of metallicity of our own Sun, which of course implies that it's mostly made out of hydrogen and helium and a lot less of other materials, which of course could also influence the composition of planets in the orbit of this star. And interestingly, the star is also slowly approaching the solar system, so in approximately 43,000 years from now, it's going to be at its closest approach just a little bit over 10 light years away from us. And because of all of these strange similarities to our Sun, like for example the fact that it's a lonely star, it doesn't have any partners like Alpha Centauri does, and also because originally we've discovered planets here a few years ago, this star has always been sort of the primary source of investigation, speculation, and interest when it comes to search for extraterrestrial intelligence and of course potential colonization of any kind of a star system. As a matter of fact, several different projects looking for extraterrestrial intelligence focused on this star in the past, one being this one right here, Project Phoenix, and one being the older project known as Project Ozma. But of course nothing has been discovered so far, and at the moment it doesn't seem like anyone is trying to communicate with us or is sending any artificial signals from the star system. But because the star is so stable and also so similar to the Sun, and also because back in 2012 we've discovered several planets here, with originally 4 different planets assumed to be in orbit of this star system, Tau Ceti has been actually growing in popularity and has now become one of the most interesting stars in the vicinity, with some of the recent papers suggesting that this particular star system contains 8 different planets, kind of similar to solar system in that sense. And interestingly, at least one of these suggested planets seems to be in the habitable zone of Tau Ceti. And so it's really interesting to kind of explore this system once again, just to find out what we've learned about it in the last few years. Now, first of all, these original 4 planets discovered back in December of 2012 were actually discovered by looking at the slight wobbles of the star itself. They weren't discovered by looking at the shadows like we usually do, and so in this case by investigating slight changes in the velocity of the star. With the velocity changes of about 11 meters per second, the scientists were able to observe the original 4 planets, with all 4 planets being what you would call a super-Earth or a mini-Neptune. A lot more massive than planet Earth, but not as massive as, for example, Saturn and Jupiter. But as the scientists kept studying the data coming from this particular star, additional hints of other planets started to appear as well, including what seems to be a Jupiter-like planet at a slightly farther away distance of about 3 to maybe 20 astronomical units, and also several other objects that were definitely disrupting the motion of the star, suggesting more undiscovered objects. Now in 2017, 4 of these planets were officially confirmed, so now we're pretty certain there's at least 4 planets here, but the other 4 were only recently identified, and this was actually using a completely new mathematical algorithm known as dynamite for short, the study about which you can find in the description below. And what this particular algorithm allows us to do now is to use statistical analysis from other discoveries to try to predict the existence of other potential planets in a typical star system, by knowing which planets already exist and how they would most likely interact with nearby planets. All of this, of course, is based on thousands of other objects we've discovered so far, and all of the other planetary interactions we've collected over the past few decades. And so using the dynamite algorithm, the scientists behind the paper in the description were able to find out the most likely locations of 4 other objects that are most likely present here, and one of these objects seems to be right in the middle of the habitable zone, at a distance of about 0.7 astronomical units away from the center of the star. So basically somewhere right here. And although we obviously know nothing about the planet or what it's made out of, and obviously we don't even know if it's a super-Earth, if it's a rocky planet, or if it's some sort of a strange mini-Neptune-like object with a lot of hydrogen and helium on the surface, the presence of this planet in the habitable zone is still quite exciting. Just the idea that there could be a planet in a habitable zone around one of the most exciting stars in the vicinity is definitely a good enough reason to continuously investigate the star system to actually discover if this planet is truly there and what it might actually consist of. Now, based on all of the radial velocity observations and all of the other analysis, this particular planet is still going to be more massive than planet Earth, with all of the other planets also being at least 2 to 3 masses of Earth as well, possibly even more. It's a lot more likely that these are really massive planets, potentially even small gas giants, that don't really resemble Earth at all. They might be actually somewhat similar to Neptune and Uranus. And all of this is simply based on the idea that the star system here has very low metallicity. It doesn't really have as much silicon, as much iron. It doesn't have as many materials to make these terrestrial planets like what we have here in the solar system. But because we're still learning about how star systems are created and how planets form, all of this could be completely wrong. We could end up finding some really exciting planets here. Which is why, of course, it's kind of important to investigate the system when the new telescopes become available. However, one interesting difference about Tau Ceti compared to the solar system is that it also seems to possess about 10 times more dust, and obviously more asteroids and possibly more comets than the solar system. This also implies that various impact events would be a lot more common on these planets. Now, this might not mean anything, but it also could mean everything. It could mean that life might not actually have a chance to establish itself here. And at the same time, kind of similar to the asteroid belt around the solar system, the Tau Ceti system also seems to have a really large debris disk as well. And although seeing these disks is actually kind of common around other star systems, because Tau Cetus is over 5.8 billion years old, it sort of makes this a very interesting object to investigate because not a lot of old star systems, or at least none of the ones we've seen so far, seem to have these debris disks. Usually this is something that's common around young star systems, not really old systems. And so far, it looks like we found 7 either super-Earths or mini-Neptune-like objects, with at least one of them right in the middle of the habitable zone where we expect to have liquid water, but also a really large gas giant on the outskirts, somewhere near the so-called debris disk. In that sense, it's actually somewhat similar to the solar system as well, where we have Jupiter more or less right after the asteroid belt as well. And naturally, because of all of these similarities to the solar system, because of all of the planets we've discovered here, and because the star is actually kind of calm, very similar to the Sun as well, doesn't really produce a lot of flares, doesn't really do a lot of activity like some of the other nearby stars, and also because this star system is slowly approaching the solar system and is going to be doing this for the next 40,000 years, this is obviously one of the most exciting star systems we have near us. Both for the reasons of potential exploration, for the reasons of potential life here, and also because by studying these solar analogs, we might actually understand a lot more about how various star systems form, and obviously start looking for signs of potential life around these planets as well. If life can exist anywhere, it's probably going to exist here. And if life doesn't exist here, well, in that case, it's probably something to do with that other video I made recently that does speculate that life on Earth might have been just really lucky. You can check it out somewhere above my head. But anyway, until we actually confirm the existence of these planets with some of the future observations, and until we actually know what they're made out of, and what sort of composition they have, there's really nothing else we can do for now. These predictions are still very preliminary, but having another star system with 8 planets is actually kind of exciting. Either way, it's very likely we're going to be returning to Tau Cetus once a new study comes out, either proving or disproving these findings, and also we're probably going to be talking about this once we actually get more observations from other telescopes, like the James Webb Telescope that's going to become operational relatively soon. Hello wonderful person, this is Anton, and today we're going to be talking about a discovery of a pretty interesting and somewhat unusual exoplanet known as Coconuts 2b. That's right, it's called Coconuts. But the name itself has nothing to do with the shape or the composition of the planet. It is nevertheless a very interesting exoplanet that was recently directly imaged by the scientists whose paper you can find in the description below. So let's talk a little bit more about why this planet is so exciting, and also find out why this planet is so unusual and what exactly we might learn about it in some of the future studies. Now, first of all, when it comes to discovering various exoplanets, today it's very difficult to find something that would surprise scientists. Thousands upon thousands of various exoplanets have already been discovered, and some of them are indeed quite unusual. However, finding an exoplanet about which it's kind of worth talking about is a little bit more rare now than it was a few years ago. The vast majority of all of the planets out there have actually been discovered by looking at the shadows of those planets passing in front of the parent star. This is what's known as the transit method. And because of this, the vast majority of the planets found so far are more or less kind of similar to one another. They're usually relatively close to the parent star. They also generally have a relatively short year. They usually go around the star in just a few weeks, maybe a few months, but almost never more than a few years. And all of this is of course because of the way that we look for these planets. We have to look at a certain region for long enough time to be able to detect them and to be able to confirm them afterwards. And so any extreme planets really far away, or planets that might be orbiting in a way where they can't actually pass in front of the star, are generally not visible using these methods. And because of this, there are several other methods, successful methods, that could be used to find exoplanets. The other very successful method is this right here, the radial velocity or the wobbling method. This is when the planet is really massive and it causes the star itself to sort of move back and forth as it travels across the galaxy. But this of course requires a very massive planet, and so all of the planets discovered using this method are normally more or less quite extreme in terms of mass, but also usually are really close to the star itself. In order for them to pull at the star and to make the star wobble this way, they do have to be relatively close to the star itself. Some other successful methods sometimes employ the technique known as the gravitational lensing, but this here relies on a pure luck. The star and the planets have to pass in front of a distant object in order for this to be visible. And because of this, this usually only happens once per million years for a single planetary object. And there are actually a few more methods that we're not going to be mentioning today because I've talked about them in some of the previous videos, but we'll talk more about a lot of these in some of the future videos as well. But there's one method in detecting exoplanets that is actually kind of exciting. This is of course the so-called direct imaging method. This is when you literally get to see the planet itself. It's not showing us the shadow, it's not a gravitational lensing effect, it's the actual planet itself. Now normally for direct imaging methods, the scientists somehow have to get rid of the light from the star itself. And this way you can usually distinguish a tiny object really close to the star, assuming that the object is bright enough or assuming that it emits enough, some sort of a light, for example infrared light. But a lot of other scientists have been trying to perfect this method or to try to use it in different ways as well. About a year ago, back in 2020, the researchers from University of Hawaii published this paper right here, where they created a new method known as the Cool Companions on ultra-wide orbits, the method they refer to as coconuts. I guess because it's Hawaii and because it's easy to remember it. And back then they discovered their first object using this technique, the planet they refer to as Coconuts 1b. And just as the name Coconut suggests, this object has to be on a very wide orbit away from the parent star, with the planet being relatively cool in terms of temperature, or at least being some sort of a substellar object, such as, for example, a brown dwarf. But the main difficulty here was basically trying to figure out if these objects are connected to one another, or if they're just separate objects moving across the night skies. And so by using a thorough analysis of their motion, they were able to see that these are co-moving objects, they're moving in the same direction, thus implying that they were connected to one another and were gravitationally connected to one another, thus forming some sort of a star system. But now, just over a year later, they discovered the second object using this very interesting survey, with this one also being the closest planet we've ever imaged directly. The planet you see right there, known as Coconuts 2b. Now as you can see, it's a very dim object. It's also almost impossible to detect using almost any telescope. You actually need a very specific infrared observations in order to be able to even see this. And so how exactly were they able to see this object? Well, first of all, this is a gas giant, very likely about 6 to maybe 7 masses of Jupiter. But unlike our Jupiter, it's also relatively young. It's maybe anywhere from 150 to maximum 800 million years old. Because of this, it still has a lot of different isotopes on the inside that are heating up the planet quite a lot. Our Jupiter was very similar to this as well a long time ago. And because of all of this heat coming from the inside, it's maintaining the temperature of this planet at something like 160 degrees Celsius or about 320 degrees Fahrenheit. Or as the scientists themselves mention, it's basically similar to the temperature when you're baking something in your oven. And because of this, it produces quite a lot of infrared light that's visible from relatively far distances, assuming that you have an infrared telescope to see it. And so to work all of this out, the scientists essentially combined the databases from various surveys that looked at the universe in different light spectra and have collected terabytes and terabytes of data already. So for example, they used the Gaia telescope's observations of the motion of stars, and then combined them with the observations from the Wide Field Infrared Survey Explorer, also known as the WISE spacecraft, that was able to create an entire night skies by using its infrared observations, and the data from all of these observations are still even used today. And so by combining these various surveys and various observations, they were able to confirm that these two objects are first of all in the same star system, but more importantly that the Coconuts 2b is an actual planetary object that seems to emit a lot of infrared light visible from 35 light years away from us. And because of this, this makes this the closest directly observed planet ever. Which is already a pretty exciting discovery because it means that scientists will now focus on this planet to try to identify and study its atmospheric composition. But this system is exciting for a lot of other reasons as well. So first of all, although it might not look like they're far from one another, the distance between these two objects is quite dramatic. This is believed to be the second farthest planetary object to its parent star. Coconuts 2b is about 1/10 of a light year away from the star, around 6,400 astronomical units. And that's nearly 1,200 or 1,300 times farther away than Jupiter is from the Sun. Which of course means that from that distance, the star itself probably looks like a tiny red dot. Here's the artistic representation of what all of this might look like. Moreover, because of the distances, a single year on this planet is about 1.1 million years on planet Earth. And so naturally, it's sort of unknown right now how such a planet could form, and more importantly, how it could actually stay in orbit for so long without being captured by something else. Or maybe it is a captured object, and if so, where did it come from? At the moment, there are no actual answers to any of this. At the same time, this is also the second coolest exoplanet discovered so far in terms of temperatures, and in case you were wondering, the record holder is still this sub-brown dwarf you see on the picture. This is still the coldest planet we've discovered. It's colder because it's much older, and also because it's orbiting a white dwarf. It's also the second farthest object from its parent star, because this object right here still holds the record. It's still slightly farther away from the parent star than the planet Coconut 2b. But unlike other exoplanets, because we can actually directly see this one and also study its light by looking at it without using any other techniques, it really represents a perfect opportunity for the scientists to try to figure out, first of all, how various gas giants form, while also trying to figure out how exactly such distant planets form in various star systems as well. Of all different gas giants out there, this one is definitely one of the more extreme examples and definitely requires a very interesting explanation. Something that currently does not exist. And at the same time, another interesting question here would be the moons. This object very likely has a lot of moons, and also because it's warmer, some of these moons, if they're close enough, might have very interesting conditions on the surface. They're not going to be habitable, but they're still going to be much warmer, or at least somewhat warmer, than the moons around Jupiter. And so definitely a lot of intriguing investigations and potential future studies for this unusual object known as Coconuts 2. But I'm also looking forward to discovering what Coconuts 3 is going to be. Now, it's important to understand that these are not new discoveries. This planet was already found back in 2011 by that WISE survey I mentioned previously, but it's only now that the scientists realized that these two objects are actually in the same star system. And so there are probably a lot more of these objects already discovered by previous surveys that we're going to be learning about in some of the future videos. Hello wonderful person, this is Anton, and today we're going to be talking about rogue planets and the possibility of one rogue planet somewhere out there having a moon that might have habitable conditions on the surface. Or in other words, could we hypothetically have habitable moons around rogue planets, a moon possibly similar to Ganymede, to Europa or Titan, that contains really large liquid oceans underneath the ice shelf on top? And a moon that could potentially one day create life on its surface or within its oceans. And this is exactly what one of the recent studies, that as always you can find in the description below, decided to investigate and to simulate. But let's start with the idea of rogue planets first. Interestingly, we don't generally think about rogue planets very much, and we don't really get to investigate them much, mostly because they're so extremely difficult to discover. But hypothetically, at least according to recent studies, for every star in our galaxy, there should be at least one rogue planet somewhere out there. This of course suggests that in a typical galaxy we might be able to find anywhere from 200 to maybe even 400 billion rogue planets just sort of orbiting around the galaxy. But because they're so difficult to find and because there haven't really been that many discovered so far, obviously we don't really know much about them, but also we don't generally think about them. When we don't see something, we generally don't really think of it as something that's very common. That's sort of human psychology. But in reality, they're extremely common, but obviously very difficult to find. Some of the ones that have been discovered so far were either found using various infrared surveys, such as, for example, the famous survey known as WISE, with others being discovered using other telescopes as well, including Hubble, although with barely anything visible in the actual image. Yet some other ones being discovered through various gravitational lensing effects when, for example, a rogue planet passes in front of a distant star. So in that sense, rogue planets are definitely a real phenomenon, they definitely exist out there, but discovering them is still relatively challenging. And because so many of them are expected to be relatively close to the solar system as well, with some of them probably just being almost completely invisible to us, trying to discover more of them is of course of interest to us as well. But the question that was being asked in this particular study is really in regards to if such an object, and this is what it typically would look like if you were to find it somewhere in space, could potentially have habitable conditions around one of its moons. But just like a lot of other objects in the galaxy, rogue planets can be generally generated using various methods. Some of these rogue planets are probably just planets that were kicked out from typical star systems. We believe one such rogue planet probably exists and came from the solar system a few billion years ago. We just don't really know what happened to it. This is one of the theories that was discussed on the channel a few years ago. On the other hand, we also have rogue planets that can be technically created from the smaller amounts of typical gas. Several such objects are already known, and this one right here, known as OTS-44, seems to even contain roughly around 10 Earth masses of material orbiting around the central object that's going to become a rogue planet in the future, which makes this very similar to a Jupiter-like or a Saturn-like system. And so could such a system eventually form moons that could maybe possess conditions somewhat similar to what we would find on Europa, on Ganymede, or even on Titan and Enceladus? Essentially an ocean kind of covered by the ice shelves with somewhat active ocean underneath, and possibly even some other conditions that could hypothetically create life on those objects. And so in this particular study, the scientists decided to simulate this using various mathematical models, and in a nutshell they sort of created this. Although this is just my interpretation of this. They took a rogue planet that's somewhat similar to Jupiter in mass and they placed a moon around it, with the moon itself being relatively similar to planet Earth in mass. They then decided to find out if it's going to be at all possible for this moon to first acquire necessary atmospheric conditions to potentially have habitable world on it. And so, for example, would it be possible for this object to start forming water somehow? Would it be possible for this object also to have some sort of a greenhouse gas effect? Could it also somehow sustain the temperatures for long periods of time and thus have liquid water inside of it? Or just underneath the ice shelf at least? And the atmosphere of this moon was essentially approximately 90% CO2 and 10% hydrogen. Now, how would water be produced from this? According to the scientists, even without the solar radiation, it would still be possible for various types of chemical reactions, including reactions that create water, to happen through the activity of cosmic radiation. So, as cosmic rays bombard this moon, they will actually still form various chemical compounds. And according to their calculations, even though it's not as efficient as, for example, solar radiation, it will still produce some water. It's about 10,000 times slower, but it's still definitely possible. And as this water is generated, it even has a chance to then maintain its liquid form. Although naturally most of this liquid water would be underneath some sort of an ice shelf. But how exactly would it actually maintain the heat? Well, in this case, the scientists determined that there's another way for this moon to actually receive heat, through tidal effects. And I actually tried to recreate this using this simple model here as well. In this case, this moon is slightly elliptical in its orbit, and it also has another partner around as well. By being in a certain orbit, it can then start receiving just enough tidal heat effects that will start creating some really interesting conditions on the surface. Now, as you can see, the temperature here doesn't actually stay constant, it goes up and down quite a lot, but occasionally it even reaches temperatures where the ice technically melts. And as you can see in this particular simulation, the planet itself only has ice in certain parts. It's not even entirely covered in ice, with pretty much all of the energy coming from the tidal effects from the Jupiter-like object near it and from its neighboring partner. And so all of this is entirely the result of tidal effects. And because today scientists believe that this is exactly how the heat is generated inside Enceladus, Europa, and possibly even other moons of Jupiter and Saturn, which is also the main reason why scientists believe life can actually exist there, there's of course no reason not to believe that this could also happen around the moon of a rogue planet. And for as long as the orbit stays relatively constant for millions and billions of years, and also for as long as the atmosphere itself does not change too much, the chance for having stable conditions here increases dramatically as well. And by having a carbon dioxide atmosphere or atmosphere of, for example, methane, there's also a possibility for having greenhouse gas effects, which is exactly why this object here is not covered in ice. The oceans here are partially uncovered because the temperature is a little bit warmer because of the greenhouse gas effect from CO2 and from methane contents. But there are still two important shortcomings in all of this. First of all, the fact that the water itself is not going to be easily created. First of all, the fact that the water is still going to be dependent on the amount of cosmic rays received, and so the longer the moon exists out there, the more likely it's going to produce more water. But it's still of course unclear if this actually can happen because we've never observed this in nature. This is only a mathematical model. On the other hand, we're still not even sure if rogue planets can form moons, and if so, what kind of moons they end up creating. All of the examples we have so far of planets and potential moons are from star systems. There's always a star, and maybe the star is necessary for these types of moons to develop. So in other words, it's still a little bit hypothetical. Nevertheless, it's still a pretty intriguing study, and a study that we'll probably talk about again once we discover more rogue planets out there, and possibly rogue planets with actual moons around them. Hello wonderful person, this is Anton, and in this video I wanted to discuss this somewhat fascinating topic of extraterrestrial rain. But not necessarily water rain, any kind of rain. Rain of all sorts. And more specifically, we're going to be focusing on this paper that came out really recently that tried to identify what sort of raindrops would be forming and what sort of raindrops we can expect on various objects somewhere out there outside of planet Earth. Something that honestly fascinates me quite a lot. So for example, if we look at this procedurally generated world, we see that there's some liquid here. And because we see this liquid, we can kind of assume that there's probably some sort of a liquid cycle. Now we don't really know what this liquid is, but something has to replenish it once in a while. If we look at the nearby world here, this beautiful gas giant you see in the distance, it also seems to have some sort of a cycle, but we don't really get to see this. But today we know that a lot of these gas giants also have their own liquid cycles on the inside, and they have their own types of rain. For example, not so long ago, some of the NASA scientists released this paper analyzing the marsh balls, or these really large hail-like formations made out of ammonia and water mixture that very likely form on Jupiter and possibly even Saturn, but eventually evaporate as they fall closer and closer to the center of the planet. Something that very likely happens in the upper regions of Jupiter and Saturn, and something that also then mixes a lot of the materials in these upper atmospheres. But then some other studies also analyzed planets like Neptune, and they discovered that in these planets we can expect something similar to a carbon or actually diamond rain. So the pressures and the actual materials on the inside will start forming a kind of a diamond-like cycle where a lot of these miniature diamonds will form drop-like formations and will slowly fall toward the center of the planet. And this is something that a lot of scientists today actually think happens on pretty much most gas giants, including Jupiter and Saturn. Meaning that objects like Jupiter might actually have several types of rain in their atmospheres. But naturally this is not something we can see, of course, this is only something we can kind of mathematically predict. Kind of similarly to how the scientists today, based on the observations from Venus, can predict that it probably has sulfuric acid rain. And some scientists also suggest that there might be some other more extreme types of rain closer to the surface, specifically rain that might be even difficult to imagine. In this case I'm referring to supercritical carbon dioxide rain. But that's actually very speculative, mostly because the surface of Venus is still very difficult for us to see. And then of course there are several exoplanets discovered so far that might possess anything from metal rain or iron rain to titanium rain to even just rocky rain. So depending on the conditions here, a lot of different planets can actually have very different cycles functioning in a very similar way to how a water cycle functions on planet Earth. With one of the more interesting discoveries in the last few years, and one of the most well-studied planets being this one right here known as HD 819733b, that a few years ago the scientists analyzed and discovered that it very likely has glass rain, with an extremely rapid atmosphere with a lot of different activity on the surface, including of course this very unusual glass liquid cycle. Back then NASA even made this kind of a funky poster that you can actually download and print for yourself, sort of promoting this planet as if it's an object we can one day visit. Although personally, I don't think that would be a place I would want to visit anytime soon. And so with so many different types of rain on so many different planets, including the ones in the solar system, the scientists are of course kind of curious to see how these types of rains differ from one another, or if there's some sort of a commonality to all of them. With one specific question that actually needed to be answered, being the shape and the size of the actual drops. Are these drops going to be different in size? If so, how are they different? And are they going to be different in shape? And if so, how? So in other words, let's just say we imagine ourselves on that glass rain world. Is the glass rain going to be very similar to the type of rain we get here on planet Earth in terms of shape, size, and the general velocity of raindrops? Or are they going to be these really huge chunks or possibly really tiny pieces completely difficult for us to imagine? Or more realistically, let's just say we wanted to find ourselves on the surface of Titan, which hopefully one day we will. It just so happens that Titan is the only other object out there where we're absolutely certain there is a cycle, there is a liquid cycle. This is the object that does contain lakes, it's an object that does have rain, and it's an object that has an active atmosphere. So even though for gas giants like Neptune, Saturn and so on, we're kind of speculating there's rain, for Titan we're absolutely certain there's rain. And for Titan, just like for those other objects, the rain here is not water. In this case, it's methane. And so if the rain is made out of methane, we will actually produce different types of raindrops. Is the shape going to be different because the molecules are different? Is the speed going to be different? Are they going to be dramatically different in size? And, well, basically a lot of other questions in regards to what happens to these raindrops as it rains on Titan. And so the scientists behind the paper you can find in the description decided to try to answer these questions aiming at the objects here in the solar system. So objects like Titan, objects like Jupiter and Saturn, and also objects like Mars with hypothetical rain that might one day happen there as well, and possibly did happen in the past. And while the major discovery coming out of this paper is that rain, for the most part, seems to be more or less the same no matter where you go, no matter what it's made out of, and no matter how big or small the planet is. In other words, this is some sort of a universal experience for all objects in the universe, at least the ones that have any kind of a liquid cycle. But obviously all of these cycles will also depend on the clouds. Now clouds generally are extremely difficult to model or to try to study. We don't really even understand them on Earth very well just yet. But turns out trying to model rain is actually not as difficult. And so by starting with the raindrops, we can then sort of try to extrapolate this to the more general idea of the cycle on a certain planet. In other words, this is actually a really important step in order to understand how various liquid cycles might work on other planets or other moons like Titan. But first of all, for the cycle to function correctly, such as for example the cycle on Titan, the raindrop obviously has to make it to the surface. And so obviously if the raindrop is too big in size, it's not going to survive the trip to the surface and it's most likely going to fall apart into smaller raindrops. But if the size is too small, it's going to disappear because it's going to evaporate on the way to the surface. Kind of like what we believe happens on the gas giants. So here the raindrops evaporate and bring some of the materials closer to the center of the planet. But because Titan has liquid on the surface, it means that the raindrops here have to be very specific in terms of size and shape. And so there has to be some sort of, as the scientists refer to it, Goldilocks zone for basically the shape and also the size of raindrops. Now let's start with the shape. So apparently as the raindrops fall, at first they start as spheres, but as they get closer and closer to the surface, they acquire this shape that sort of resembles a burger bun. And it seems that this shape is universal no matter where you go, no matter what the actual drop is made out of. So if we go to Titan, we'll find methane that is shaped the same. If we go to some distant planet somewhere far, far away, we'll probably find something similar in shape. And although smaller raindrops do actually have a spherical shape, as they grow in size, they become these miniature buns, with the average maximum size on planet Earth being roughly around 11 millimeters. But what about Titan? Well, the shape is still going to be the same, but because the gravity here is much lower, the size of the drop is going to be 2 to 3 times larger. Now that's actually kind of surprising because in terms of the total mass, Earth is way more massive than Titan. This is about 2% the mass of planet Earth. And so the gravity here is also much weaker. On Titan the gravity is about 8 times weaker than planet Earth. While at the same time the surface pressure on the surface is higher than planet Earth. So I personally thought that maybe the drops here would be way bigger in size, but turns out that that's not really correct. The size is only a little bit bigger. As a matter of fact, these were the biggest raindrops that they were able to simulate. Once again, here's the one from planet Earth for comparison. And by the way, this is actually really zoomed in, so in reality it's only about this big, it's only about like 1 inch in size. Then if we look at objects like Jupiter and Saturn, we'll find that Saturn has really similar in size and in shape raindrops as planet Earth, with Jupiter having slightly smaller ones, mostly because of the higher gravity and obviously much higher pressures near the center as well. And lastly, hypothetically for planet Mars, if it were to have rain on the surface or if it had rain in the past, the raindrops were slightly larger than the ones we have on planet Earth. And so here's how all of this looks like if we were to compare it to planet Earth. Now this is a little bit surprising for, I guess, several reasons. The first reason, of course, being the fact that you would expect these raindrops to differ dramatically based on the element, of course, and also based on the gravity, based on the atmospheric pressure and so on. But in reality, what the scientists think is happening here is that the main property of the raindrops that determines their size and of course determines their shape is the surface tension of the material. Surface tension, of course, being that fundamental property of all liquids that allows them to shrink into the smallest possible surface area and to kind of stay in that particular shape until more liquid is introduced. Here's a really awesome video showing you how the surface tension of this water droplet is actually going to affect the droplet as it splits in two. Notice how it instantly assumes a spherical shape. And the surface tension for water is really high. It's a lot higher than the surface tension for methane. Because of this, the droplet for methane can actually expand to larger size. But surprisingly here, the material itself does not really influence the size that dramatically. Even though the surface tension of water is about 14 times higher than methane, as you can see, the size difference for all of these droplets is really not that dramatic at all. And so the conclusion from the study is that, well, it's not entirely clear why such an unusual uniformity exists for all droplets of all materials. No matter what the rain droplet is made out of, whether it be some sort of liquid iron, glass, methane, or of course water, it seems to possess similar shapes, it seems to also possess similar size, at least to some extent, and it obviously also seems to possess other properties like, for example, evaporation and, of course, formation of liquid bodies on the surface. Which of course also means that our imagining of, let's just say, some sort of a lava world where there is a lava rain with some really unusual extreme weather conditions on the surface would not really be far off if we imagined it as very typical rain on Earth. Or basically lava rain here would not really be that different. At least not different in terms of shape and what it does to the surface. And it seems that now we can actually even predict some of these properties. For example, the speed of the rain, how fast it falls toward the surface, mostly depends on the surface pressure and the gravity of the object. So if we go back to Titan here the raindrops very likely fall really slowly toward the surface because the gravity is much lower, but also because the pressure is much higher. Then the other question of whether the raindrops make it to the surface and create some sort of a liquid or not can be determined by studying the atmosphere, and specifically by studying atmospheric conditions, pressure, temperature, humidity, and so on, and determining whether the raindrops evaporate in the atmosphere or whether they make it to the surface. And so overall, this study is actually pretty brilliant in presenting us with this relatively thorough analysis on how we can potentially predict what happens on other objects. So now, by using these techniques, hypothetically the scientists could predict if a certain planet does indeed have some sort of a lava ocean, glass ocean, or maybe even diamond ocean, or possibly even predict some of the other atmospheric effects that all of this rain might form. But for now, it's still kind of difficult to predict and to analyze some of these objects, mostly because we still need to have better telescopes. And for objects like Titan, well, we actually have to have a mission here to land and to try to investigate what happens to all of these liquids by looking at them directly. And one such mission is going to be launching in approximately 6 years from now, with the estimate of arrival being 2034. Now this mission is going to be super exciting because it's also going to be a kind of a helicopter, but I guess it will still have a long time to wait before this actually happens. And so what sort of a surface Titan has, what sort of rain it has, and what kind of liquids it has on the surface is not really going to be a question we're going to be answering anytime soon, but it is a question we're going to be answering at some point in the future. Hello wonderful person, this is Anton, and today we're going to be talking about a pretty interesting discovery that suggests that planets do change quite dramatically over time. And all of this is based on all of the observations of over 4,000 different planets we've discovered so far. And what this implies is that planets like Neptune eventually transform and evaporate into something a little bit more similar to a typical super-Earth, which then can potentially change into something similar to planet Earth. Now all of this is still preliminary, but the discovery is nevertheless really interesting. And all of this is actually based on a simple question. It seems that of many different planets we've discovered so far, only some of the exoplanets are similar to something we see in our own solar system. There's actually a surprising amount of different exoplanets that we found that are very difficult for us to imagine simply because they're very different from anything like planet Earth or even gas giants like Neptune, Uranus, Saturn, and Jupiter. As a matter of fact, here you can see that Jupiter-like planets are somewhat rare. Now this particular image is a little bit outdated, but the actual fractions haven't changed very much. A much more common type of a planet is more similar to Neptune and Uranus. We've also found quite a number of Earth-like planets, and even some planets a little bit smaller than Earth. But the vast majority of planets we've discovered so far, or the vast majority of exoplanets, are basically in between Earth and Neptune in mass and in size. These are so-called super-Earths, or sometimes known as mini-Neptunes, and they essentially represent the largest number of all of the exoplanets found. They also represent the largest numbers of planets per star on average around a typical star. And so here is an example from Kepler-62, with one potentially terrestrial planet, but the rest being either super-Earths or possibly mini-Neptunes. And because of this, it was always intriguing to us, why is it that our solar system doesn't seem to have any of these super-Earths? There were a lot of different explanations proposed, like for example one of them involved an early major collision between various super-Earths that possibly existed in the solar system that may have actually resulted in a lot of material getting recycled and eventually forming the 4 terrestrial planets we have today, with the rest of the material probably just settling somewhere in the asteroid belt or possibly getting kicked out of the system completely. But this particular explanation is the most dramatic one I have, and it doesn't obviously answer everything and has a lot of questions that left unanswered. And so because of this, there's this unusual mystery of the missing super-Earths and missing mini-Neptunes from the solar system. At the same time, the scientists have always speculated that there's actually some kind of a relationship between super-Earths and mini-Neptunes, a relationship that might also depend on the star they're orbiting, while also suggesting that maybe the star somehow influences the evolution of these planets and essentially forces them to transform over billions of years of orbiting in that particular star system. Also suggesting that there's actually a correlation between the radius and the mass of a planet and the age of the star. All of these speculations suggested one thing. It suggested that some of these planets we've discovered may have evolved quite dramatically over time, and most likely way more dramatic than anything we have in the solar system. And at the moment, the only way to kind of try to prove this speculation is to literally look at all of the planets we've discovered and to try to find if there's any relationship between, for example, the age of the star and the actual planet orbiting that star. And the other related speculation that scientists had for a very long time is in regards to something known as Chthonian planets. These are the planets that have been essentially evaporated by the solar radiation from the parent star and lost a lot of their mass to the outskirts of that particular star system. Essentially here we're talking about shrinking planets. Planets undergoing some dramatic change simply because of the radiation from the star. But despite the fact that we think that this process exists, we still have no idea how long this might take and how dramatic it might change a planet. Simply because it's kind of difficult for us to study all of this without having more data from other exoplanetary systems. But because we've discovered so many different mini-Neptunes and super-Earths in the last few years, we now actually have enough data to start making certain assumptions and to start testing them scientifically. And so with the discovery of over 4,000 confirmed exoplanets, the scientists essentially combined the data from the Kepler telescope and most recent release of this data, and combined it with the data from the famous ESA's Gaia telescope that studies the motion, age, and a lot of other characteristics of billions of different stars, which then allow the scientists to combine all of the data and to see if there's any correlation between the age of a star and size and mass of a typical planet. And as you can probably imagine, they made a surprising discovery. A discovery that would be impossible to make if we were just looking at one single planet, simply because we're only getting a single snapshot of the entire timeline of this planet. But by looking at hundreds and even thousands of these planets, things become a little bit more clear. And what these results suggest is that, independent of the actual location of the planet around the star system, it seems that many of these planets do lose quite a lot of mass, with the majority of planets transforming from something similar to a mini-Neptune to something similar to a super-Earth. And to help you visualize all of this, let's just say that this is a mini-Neptune and this here is a super-Earth. Obviously, a real mini-Neptune would be a little bit smaller than Neptune, and a real super-Earth would be a little bit larger than planet Earth. And so what they discovered is that it seems that as the star gets older, the total ratio of mini-Neptunes to Earths seems to actually change to the point where mini-Neptunes start to disappear and more super-Earths start to appear, as if some of the mini-Neptunes transformed into these super-Earths. Or in other words, as the star ages, it's a lot more likely you're going to find more super-Earths around those stars than you're going to find these mini-Neptunes. And the only reasonable explanation, although possibly not the only explanation, is that these planets probably evaporated and decreased in mass and size, turning into super-Earths. And so what this study is really suggesting is that we're basically looking at a kind of an evolution of these planetary systems. As they age for billions and billions of years, some of the planets evaporate to the point where they lose several masses of planet Earth in total mass, most likely just gas like hydrogen and helium, and thus lose a lot of size and a lot of mass in the process. And so even though in the beginning of the star system a planet might resemble something like this, it will eventually start shrinking, getting smaller and smaller, and will also reach a point where it might turn into some sort of a relatively large terrestrial world. In this case, slightly more massive and slightly larger than planet Earth, something that we usually refer to as a super-Earth. Now at this point we don't really know what's going to happen to these planets, but chances are that they're going to stay terrestrial or not really gas planets anymore for the rest of the existence of that star system. But for as long as the planets here still have some sort of a gas envelope or even some sort of a liquid surface with a lot of liquid on the surface, chances for these planets to transform into, for example, something a little bit more similar to planet Earth or a little bit more terrestrial are going to be much higher. And I guess one of the major discoveries from this paper is that it seems to happen on really large timescales. We're talking about billions and billions of years here, not just something that happens in the beginning of the star system. And naturally, the more starlight the planet receives, or essentially the more illumination it gets from the star, the more likely it's going to lose more mass. And what this kind of presents to us is this idea of planetary evolution on the scales of billions of years. This of course also suggests that a lot of the planets we've discovered so far, especially a lot of these super-Earths, might transform even more. And this also basically explains to us that when we find a planet, we're not really looking at its final state just yet. These planets will change with time, obviously not human times here, we're talking about billions of years, with some of these planets probably transforming quite dramatically to the point where, even though they might be uninhabitable and possibly difficult to survive on in the beginning, they might become more habitable after billions of years. And so all in all, this is actually a pretty interesting discovery and definitely not something that we expected to find. But at the same time, it's a very exciting discovery and will most likely lead to a lot of new speculations, a lot of new ideas, and a lot of new papers. Hello wonderful person, this is Anton, and today we're going to be talking about this new study that seems to have identified a completely new type of a planet that could potentially be habitable. And in this case, the scientists refer to these types of planets as the Haitian worlds, with a lot of these worlds falling under the category known as the mini-Neptunes. But the most exciting part of this particular study, and in this case the most exciting part of the analysis, is that there seem to be so many of these planets out there, with some of them being the most common planets we've discovered. So this is actually a pretty interesting study and a pretty interesting analysis. And so let's start with the idea of what these planets are like and what probably happens on their surfaces. Starting with this right here. As of today, we've confirmed 4,472 exoplanets, with nearly 8,000 other planets being candidates, meaning that they're probably going to get confirmed at some point in the future. And of these thousands of different exoplanets discovered so far, some of them have actually been much easier to find and some of them kind of stand out. And a lot of those very common exoplanets don't seem to exist in the solar system either, so we don't really know much about them. And generally a lot of these exoplanets are divided into the rocky planets, with the hot ones being referred to as the lava worlds, all sorts of different gas giants such as hot Jupiters, but then right here in the middle we have these ocean worlds, ice giants, mini-Neptunes, and super-Earths. And these are the planets that have been really fascinating because there seem to be a lot more of them than a lot of other planets. Way more than gas giants and even more than typical terrestrial planets or rocky worlds. But because these types of planets do not exist in the solar system, the only way for us to figure out what's happening on their surface and inside of these planets is through various hypothetical studies or through various simulations using supercomputers. Nevertheless, they do represent some of the most exciting exoplanets we've discovered so far, with one in particular already showing signs of potential habitability. The exoplanet located about 124 light-years away from us, known as K2-18b, an object that we've discussed on the channel previously, and a planet where the water vapor has already been discovered in the atmosphere, that also happens to be in the habitable zone of the star system, and that might potentially represent the prototype for these types of exoplanets, the Haitian planets. Planets that seem to be habitable, but represent something completely different from planet Earth. And that is pretty much the focus of the paper that you can find in the description below. They investigate these planets mathematically, and sort of discovered that, first of all, these planets do seem to possess habitable conditions in certain parts of the planet, while also discovering that these unusual planets might be some of the most numerous habitable worlds out there, which actually makes this really exciting. But in order to classify these objects and a lot of these planets as habitable, we of course are relying on the idea behind planet Earth. The assumption here is that the habitability comes from liquid water, so these objects have to possess a way to maintain liquid water for millions and billions of years. Which is of course why objects around Saturn and Jupiter, such as Ganymede, Europa, Titan and so on, have generally been seen as good potential candidates for potential life living somewhere inside those planets, somewhere underneath the ice caps, inside the liquid ocean. But in this particular case, through analysis, the scientists have also determined that certain mini-Neptunes, or these objects that are generally less massive and usually smaller than Neptune, yet are way bigger and more massive than planet Earth, given just the right properties, will actually contain quite a lot of different ways to maintain liquid water inside the planet underneath the thick atmosphere. Or in other words, if we were to somehow see through the atmosphere, we would probably find ourselves in a very interesting situation with a very large liquid ocean and potentially a lot of possibilities for life to form in these oceans. Oceans that would be tens of if not hundreds of times larger than the oceans on planet Earth. With the atmosphere being very different from planet Earth as well, probably very rich in hydrogen and certain other elements. Despite of all of this, the best representation of K2-18b, the prototype for these Haitian planets, at the moment makes it look like this. It's essentially an extremely large and very massive ocean world. And here's how it compares to planet Earth. With most of these planets being generally about 1.6 to maybe about 3.9 times larger in size than planet Earth, and the total mass being about 5 to 10 masses of planet Earth as well, so more massive and larger in size. With K2-18b being exactly 2.6 times larger and about 8.6 times more massive than Earth. But since it's located in the habitable zone of the planet, and since water vapor has already been discovered around this particular planet, this makes this one of the more interesting planets discovered out there. But according to the study, definitely not the only such planet, and a lot more have already been discovered and have already been confirmed, suggesting that this could definitely represent a completely new class of habitable planets that we should be exploring in more detail. Although trying to define exactly what the properties of these planets are is still a little bit difficult. So in this paper, the scientists believe that most of them are probably not really super-Earths. They're much bigger than super-Earths, but much smaller than mini-Neptunes. In other words, they represent a completely different class of a planet, with the maximum suggested size for these planets being about 2.6 size of planet Earth and about 10 masses of Earth, because after this they probably turn into mini-Neptunes. At the same time, the temperature on these planets can actually be pretty high, simply because of very high pressures on the surface and because some of them are a little bit closer to the parent star. The atmospheric temperatures can be up to about 200 degrees Celsius, so technically past the boiling temperature of water. But because of the high pressures on the surface, possibly up to about 1000 bar of pressure, the water can maintain its liquid form, and deeper in the water, the temperature will actually decrease, creating very comfortable conditions deeper in the oceans where life can actually easily evolve. But at the same time, these planets do vary quite a lot. For example, some of these planets will be tidally locked to the star. They will always be facing with the same side. And these dark Haitian worlds, as the scientists refer to them, will actually have very different conditions on the surface, potentially even more habitable than some of the other planets. At the same time, some of them will be farther away from the star and will actually form what's known as the cold Haitian planets. In this case, probably being somewhat similar to Europa, Ganymede and Titan, which overall creates quite a diversity for various habitable conditions with many of these planets already meeting the qualifications for being the Hycean planet. And even though previously we mostly focused on terrestrial habitable zone, or basically looking for planets that are similar to planet Earth that are in the habitable zone of their stars, the main suggestion in the paper is that the Hycean planets represent a much higher chance for us to find alien life somewhere out there, with quite a lot of these planets already fitting into the category. On top of this, because of their size and because of the thickness of their atmosphere, some of the future telescopes, such as the James Webb Telescope, will have a perfect opportunity to look for various biosignatures in the atmospheres of these planets. And the scientists in this paper identify several such biomarkers, with some of them visible in this graph right here, suggesting that a lot of these planets should really be the focus of future studies, in terms of this search for extraterrestrial life at least. And so any kind of a biosignature or any kind of emission coming from potential life here would be a lot easier to find around a lot of these Hycean planets compared to some of the terrestrial ones we've found so far, with quite a lot of candidates that have already been found being within about 150 light years away from planet Earth. And because of the atmospheric composition of these planets, they actually maintain their habitability in a lot of different regions around the star. They can actually maintain liquid water even if they're really far from the star, simply because of the pressures created by the hydrogen. Suggesting, of course, that even at really far away distances from the star, they'll still technically be habitable and have liquid oceans, which makes this for a pretty exciting type of planet and will most likely create a lot of exciting opportunities for future studies. But in this case, we're probably going to be looking for very different biosignatures, mostly because it's expected that the life, if it exists here, is not really going to be producing much oxygen or a lot of other similar compounds to planet Earth. The chemical emissions from the life here would be very different, with potential signs of life being things like methyl chloride, dimethyl sulfide, and a lot of other non-oxygen life-based compounds that we normally find in some of the depths of the oceans on planet Earth. And so life here would be obviously extremely different. It would be surviving extremely hot conditions, it would also be living in very highly pressurized conditions, but I guess not so different from some of the regions in the oceans of planet Earth. But in regards to potential extraterrestrial intelligence on these planets, that's a completely different question. Since we don't even understand how intelligence formed on planet Earth, we're probably not going to be finding anything anytime soon. Hello wonderful person, this is Anton, and today we're going to be talking about TRAPPIST-1 system once again, because yet again we made a very exciting discovery that both presents us with a new mystery and also allows us to study these beautiful planets, opening up a lot of new opportunities for new studies. Specifically here, the scientists discovered something unusual about the densities or the composition of these 7 planets. But in case you forgot what TRAPPIST-1 is, well, to date it's probably the most exciting planetary system we've discovered so far, located about 40 light years away from us, which is, in terms of galactic distances, is actually relatively close. This is the system discovered only a few years ago when the scientists realized that there were 7 very unique and very unusual terrestrial planets orbiting around a red dwarf, with all of the planets being relatively similar in size, relatively similar in mass, and also being located in a somewhat exciting region. 3 or possibly even 4 of these planets are in the habitable zone of the star system, with all of the planets here now officially confirmed to be terrestrial, meaning that they're not super Earths, they're not gas giants, they're actually planets like Mercury, Mars, Venus, and Earth. But all of this took years and years of observations, analysis, and thorough understanding of how orbital dynamics work around these planetary systems. Now, originally we discovered these planets via the Kepler telescope by essentially looking at the shadows passing in front of the star. This is how the scientists were able to determine the sizes of all of these planets. Knowing the size though is not really enough to determine, for example, the mass or the density. You still have to actually find the mass of these planets for us to learn anything else about them. One way of trying to discover the mass of planets is by looking at how much the star wobbles as the planet passes around the star. By measuring the amount of wobble, or basically the amount of motion of the star across the night skies, we can then determine the mass of this planet. But this usually mostly works for larger planets like Jupiter-like objects. So for a gas giant, it's relatively easy for the scientists to determine mass this way. For smaller planets, terrestrial planets, especially planets that only represent a fraction of the total mass of the star system, that method would not really work very well. You would need to have an extremely accurate telescope, which doesn't actually exist yet. Just to give you a comparison of mass difference here, the total mass of all of the TRAPPIST-1 planets represent about 0.02% of the total mass of the star system. Now that's almost nothing. That's actually kind of similar to the amount of mass in all of the moons of Jupiter compared to the mass of Jupiter. Which, by the way, does imply that these particular planets may have been created in a very similar way to the moons of Jupiter. There is actually a very unusual similarity in different orbital patterns and also just in the way that the planets behave compared to the moons of Jupiter. And so by just knowing the sizes of these planets, how did the scientists determine their mass then? Well, there's actually a very interesting method known as TTV, or transit timing variation. This method also relies on measuring the shadows of these planets passing in front of the star, but in this case, when there's another object in the star system, such as for example another massive planet nearby, it will start pulling on this planet, thus affecting when these shadows appear compared to our original predictions. So in this case, because of the pull from this planet, the transits now, the shadows, will have slightly different timing. There will be a timing variation. Now this transit timing variation is a very precise and actually very interesting method of determining the total masses of all of these planets. And so by looking at transit timing variations of all 7 planets, after only a few months, the scientists were able to calculate very precise masses of each of these planets, where the transit timing variation made a lot of sense. And now we know as a fact what the mass and the size of each of these planets is, with the recent study being the most accurate in determining both. And once you know the size and the mass of each of these planets, finding the density is just a matter of division. Dividing one value by the other, you get the total density of each of these planets. Now, what's really unusual is of course the recent discovery and the recent confirmation that the density of each of these planets is very unique to anything we've seen so far. Each of these planets seem to have extremely similar density to each other, and that's something we've never seen before, with the overall planetary density being very similar to planet Earth and also very similar to each other. It's defined as being about 8% less than the density of Earth and the density of Venus. And remember, here we're talking about 7 unique planets, 7 planets that most likely also have somewhat different surfaces, somewhat different atmospheres, and potentially somewhat different composition as well. But in this case, they do have very similar density, and that just kind of doesn't make sense right now. The reason it doesn't make sense is because of the examples we have from the solar system, and actually really from any star system we've seen so far. So just as a comparison, let's take a look at the solar system and the density of planets here. The highest density of all of the objects is our own planet Earth. The density here is about 5.5 grams per centimeter cube. Then we have the neighbor Venus, then we have Mercury, and then we have Mars, with the density of Mars being about 3.93 grams per centimeter cube. Now usually by knowing these densities, we can then determine what the composition of the planet is and also what sort of materials we can expect to find both inside the planet and possibly even in the upper regions of the planets. Now in this case, we know that Mars, for example, doesn't really have a very large iron core, whereas Mercury, despite its smaller size, probably has a much larger core. And then once we start talking about gas giants, the densities suddenly drop. With the least dense object of all being Saturn, the density here is actually less than the density of water. It's about 0.68 grams per centimeter cube. And so here, that's kind of what we expect from most of the planets in the typical star system, and for the most part we've been seeing something similar in other star systems as well. Even if you were to look at the moons of Jupiter, their densities do vary quite a lot. Not as much as the density between Earth and Saturn, for example, but still quite a lot. Between 1.83 grams per centimeter cube for Callisto and 3.53 grams per centimeter cube for Io. But somehow none of this seems to work for TRAPPIST-1 planets. Each of the planets here, despite the distances to the star and despite their location in the star system, seem to have relatively similar densities, even if their size or their mass is different from the planet next to it. And at the moment, nobody really knows how to explain any of this. There are 3 potential explanations, but none of them are really conclusive. The first explanation here is really in regards to the cores of these planets. All 7 of them might have relatively similar iron cores that are slightly smaller than the core of planet Earth, with the iron cores inside each of these 7 planets being roughly around 21% of the total mass of each of these planets. But having a core that's pretty much exactly the same as the core of the planet next to it is very unusual, or it would be almost impossible to explain this in any of the modern planetary formation theories today. Why would these planets have exactly the same internal structure? Currently, there is really no way to explain this. And also, just to give you a comparison, Earth has the core that's about 32% of the total mass, and it's that iron core that gives our planet such a high density. And it's also the biggest iron core of all of the terrestrial planets in the solar system. The second explanation that kind of makes sense is maybe because all of these 7 planets are filled with iron oxides. You know, that same stuff that makes the surface of Mars red, but unlike surface of Mars, all of this would be going all the way down to the core. Now that's a very good explanation as well, but it still doesn't make sense that all 7 of them would have this. We know, for example, that several moons of Saturn and Jupiter, such as Titan right here, do have a kind of a strange mixture on the inside, where the silicates are mixed with different water compounds and form these unusual structures on the inside that give them very specific densities. Something similar could happen if you were to mix metals, or iron in this case, with various oxygen compounds. But there should still be some sort of a density difference. It's still kind of difficult to imagine that all 7 planets would have exactly the same densities and exactly the same structures. And the last and the third explanation here is, well, it's also kind of unusual, but kind of makes more sense. In this case, the scientists imply that it's possible that the large amount of mass of each of these planets is made out of water. And more specifically, the middle planets here would most likely contain some sort of a liquid ocean. The outer planets would be made out of really large amounts of ice. But the inner planets, specifically the 3 inner planets, would have a very large atmosphere of water gas, which would also in turn increase their overall size. Kind of similar to the very thick atmosphere we see around Venus, for example. And for this explanation to work well, each of these 7 planets would have to have a very specific amount of water on the surface. It doesn't really matter what they have on the inside, they'll probably still have different cores and different iron composition, but the presence of water has to differ in order for them to have these properties that we're observing and to have the sizes and the masses that we're seeing. Which also implies that at least 3 of these planets potentially have a liquid ocean on the surface. But here on some of these planets, this would also mean that water would have to represent about 5% of the total mass of the planets, especially the outer 4 planets. Whereas if you were to look at planet Earth, our planet only has about 1% of mass being water. But of all of these 3 ideas or 3 propositions, the one about water actually makes the most sense right now. Although it's also possible that it could actually be a combination of 2 or even 3 of these propositions. So maybe there is a lot of water on some of these planets, but they also contain a lot of iron oxides as well, and possibly even some sort of an iron core. So all 3 ideas and 3 propositions currently kind of make sense. Nevertheless, all of these discoveries of TRAPPIST-1 present the star system as one of the most unique star systems we've ever discovered, with 7 planets that are extremely interesting for many different reasons, some of which of course being the fact that they probably contain liquid oceans, and also don't seem to be very different from planet Earth in terms of the mass, size, and of course density. Now whether they actually look like this picture right here, and whether we discover signs of potential life here, is unfortunately not something we're going to know until we take a look at these planets with more powerful telescopes. Luckily, James Webb telescopes should be able to tell us a lot more about this star system in the next few years. But for now, that's all we know about this unusual star system. We seem to be discovering new things about it every single time there's a new study, and we seem to be discovering new mysteries as well. But hopefully in the next few years we'll have a definitive answer about what's really happening in the star system and whether we're going to find something absolutely incredible on the surface of these unusual planets. One day we might be able to visit them, but it's probably not going to be anytime soon. But anyway, that's all I wanted to mention for now. Check out the study I mentioned in the description below and all of the additional information there as well. If you've enjoyed this video, subscribe, maybe share this with someone who loves learning about space and sciences, maybe come back tomorrow to learn something else, and maybe support this channel on Patreon or by buying the Wonderful Person t-shirt that I'm wearing right now that you can also find in the description. I'll see you tomorrow, space out, and as always, bye bye.